Welcome everyone to our Astronomy on Tap Los Angeles September event. I am Dr. Cameron Hummels, research astrophysicist at Caltech, and I will be the MC for our event tonight. Our other MC is Dr. Kaylin Henderson. Kaylin, do you want to come on?
Yeah. Hi, everybody. Good to see you again.
Kaylin is a staff scientist at IPAC, which is a NASA center on Caltech's campus. If you can't tell from his background, he does exoplanet research. And I'm really excited for our event tonight. We have a really cool couple of speakers who are actually kind of famous, both of them. So I'm really psyched about that. Well, actually, do you guys want to come on? Our speakers tonight, not a formal introduction, but our speakers tonight are Dr. Jackie Faherty, who's a staff scientist at the American Museum of Natural History, and Dr. Konstantin Batygin, who is a professor at Caltech doing research in a variety of things, but most notably, I suppose, is the whole Planet 9 stuff that he's going to talk about tonight, this undetected planet in the outer solar system, but there's reason to believe it's here. It's right. It's behind the plant. Oh, Konstantin, you're muted. FYI.
It's probably better for the public.
So this is one of our Astronomy on Tap events. We have these once a month on Monday nights. Typically they're held in a bar, but of course we aren't able to do that since COVID and all of that. So we're doing them live streamed. And the schedule for tonight will be after I finish a couple of announcements over the next couple of minutes. We'll start off with a talk by Jackie. It'll be about 15 or so minutes, and then we'll take questions from the audience. You guys can ask questions throughout the talk in the YouTube comments that are on the side of this stream, and we'll try and address those questions. And then we'll introduce Konstantin, who will give a similar 15-ish minute talk, followed by questions about Planet 9 and so on and so forth. And then after all that, we'll do pub trivia, astronomy themed pub trivia on a bunch of really cool topics, and then discuss the answers. And it's all interactive. So there are ways, and there's a website that you can go to and put your answer, and then we'll see the answer that you give, that all of you give, and you'll see what everybody else is saying. So it's pretty fun. Unfortunately, we don't have prizes because it's hard to deal with that virtually, but you'll know in your heart of hearts that you were the one who got them all right.
And it's important to remember, knowledge is its own reward.
It is its own reward. That's right. Good point, Kaylin.
So, don't be too competitive. Don't be too competitive.
In addition to this series, we also lead at Caltech Astronomy a public lecture series that happens once a month, and that's a little bit more formal. That's a 30-minute talk. And traditionally it had stargazing afterwards, but that's really hard to do with the pandemic and live stream. So we have the public lecture that's 30 minutes long. We do a little virtual stargazing where we show what's up in the sky for that month and give you an idea what you can see if you were to look out in the night sky. And actually right now there's a lot of really cool stuff to see in the night sky. So, but then after that we have a Q&A that's 90 minutes long with 4 different researchers from Caltech and the Jet Propulsion Lab to answer questions on whatever astronomy or physics or space science that you can throw at us, and hopefully we address it pretty well. So that the next one of those events will be a week from Friday. It'll be given by a researcher at Caltech and JPL named Dr. Agnès Ferté. She's a French postdoc who studies, she uses the dark energy survey to look at dark energy. And so it'll be all about what is dark energy, what implications and effects does it have on the expansion of the universe, and the implications for cosmological models and that sort of thing. So it should be really, really cool. And it'll be streamed right here. So if you look at our next events, I've already set the event for that. But anyway, okay, enough announcements. I think
I'll jump in. I'm seeing a couple of questions in the chat. We have a bunch of viewers, maybe a bunch of new viewers. So in answer to one of the questions, the pub trivia is something that we'll actually do live through Zoom, through this YouTube live link after both of the talks finish. And so, after Jackie and then after Konstantin, stay online, stick with the program, and we'll do it after all that. Also, longtime fan of the program and trivia expert Brian Federa has requested a moment of silence for my mustache. It had a good life. It had
that did disappear. That's good. That was really
the lip
abomination.
Gone back into hibernation. Thank you for acknowledging that, Brian. All right, no further announcements, I think, from the chat.
Oh, well, I have a question for everybody. So traditionally these events, because it's called Astronomy on Tap, are held in a bar. Oh, and a side note, we're only Astronomy on Tap in Los Angeles. There's actually another LA chapter that's opening up out of UCLA, but there's Astronomy on Taps in lots and lots of different cities around the world. So if you're psyched about this one, I encourage you to go to astronomyontap.org, and it lists all the events, and most of them right now are live streams. So if you're like hungry for more astronomy, you can check them out. There's some great ones all over. UT Austin has a super good one. Michigan State has a super good one. Yeah, Seattle has a great one. And Jackie, you've spoken at least the New York City one in the past, right?
And DC and Texas and Seattle and a bunch. I've done a lot of Astronomy on Tap. We should tell people, Cameron, that the three of you are on the same time zone, but I am on the Eastern time zone. So that's important for your viewers to realize. I am at 10:38, not 7:30, when you guys are all relaxed.
Well, actually, Constantine right now is in New Mexico and I'm in Colorado. So we're in mountain, but we aren't quite that late.
Oh, okay.
I drove to Colorado to escape all the fires and to go on vacation. So I'm in Colorado drinking a Colorado beer.
Oh, very
Avery,
nice.
the Reverend, a very fine beverage.
Mm-hmm.
But yeah, I'm just here for a couple of weeks. What are you drinking, Constantine?
I'm drinking this wine. It's rose colored, and it's from the place that brought us the good stuff. It's called I think the Italians pronounce it Farinelli.
Ooh.
I think that's how they say it out there.
Okay. Kaylin or Jackie, do either of you have beverages?
I had mine, but it's 10:40 here. So I finished all my drinking for the evening. But now I feel like I should go. I was drinking delicious kava. Oh. The bottle is still here. I could keep drinking it. So
sure.
I think there comes a time when you transition to I'm still drinking to I'm already drinking. So I feel like that time is now.
I have to get up and go get it, which means I would disappear from the Brady Bunch view here. And I think your viewers would wonder what happened to, that amazing box with the woman in it. So I should wait until I go blank.
Kaylin, what are you drinking?
So I actually am not drinking anything. So even though I guess we have a Nasadena Astronomy on Tap first, I think we're all in 4 different states. I have not left California, and especially when the smoke was pretty bad a couple of weeks ago, I am out of scotch. It is gone. So I have a banana. I'm gonna eat a banana.
Okay.
Things are okay. We have water and power, but I really like bananas.
I do too.
Yeah, they're great.
Yeah.
Okay.
So I'm glad y'all are doing the heavy lifting.
Yeah.
By y'all, I mean Constantine.
Yeah, I'm pretty sure it's just 50% heavy lift happening on either corner of the Brady Bunch right now. I'm not on heavy lifting. That's soft lifting.
Oh, one side note that I only recognized when I glanced at my calendar today. I believe tomorrow is Jackie Faherty's birthday.
Hey.
Oh, Cameron, you always get it off. It was 2 days ago.
Oh no!
You've missed it. Now we're farther from my birthday than we were.
Oh, okay, I'm sorry I brought it up.
You should be. It's embarrassing.
Cameron,
it's embarrassing.
So fast all the time. Time dilates. You know how it goes.
That's right.
And I want to do a little plug. We could do plugs here, right? We're allowed to plug. So I worked on a film. It's called Big Astronomy. It's about Chile, and it's about the people that work on the telescopes in Chile, from telescope operators to the people that move the ALMA arrays around, to the science engineers, to the astronomers. And it was supposed to premiere in May. It was produced, directed, written and produced at California Academy of Sciences by my dear friend Ryan Wyatt, who Constantine knows. The narrator was a wonderful astronomer named Barbara Rojas Ayala, who's a Chilean astronomer. And it premiered on Saturday. It's free for everybody. Go to bigastronomy.org and you can watch the film and download all our education materials. And we like to pretend Ryan decided to premiere the movie on my birthday. So
excellent.
You know,
Nice.
I'll put
I was on the science advisory committee for it.
I'll put the link in our description for the event so people can click on it directly. You said it's bigastronomy.org?
.org. I think it's .org.
Okay,
it could be .com, but I think it's bigastronomy.org.
Okay.
I think too, I don't know if this happens every year, but I think at least this year, if my dates are right, your birthday fell on International Observe the Moon night. I think that was also 2 nights ago.
Oh, really?
Yeah.
Well, that makes me feel good, but bad that I didn't know that.
Well, it might be one of those things that doesn't always line up.
Yeah.
You know, it's like werewolves and stuff.
Oh,
You have
right.
to ask causation or correlation.
Could be
What's
one or the
going on
other.
here, right?
Okay. I am going to introduce, unless anybody else has plugs or announcements, any other business? Okay. I'm going to introduce Jackie as our first speaker. So let's see. Where's my stuff to read? Dr. Jackie Faherty is a staff astronomer at the American Museum of Natural History. She co-leads a dynamic research group called Brown Dwarfs in New York City, BDNYC, which investigates the fundamental properties of the coldest and lowest mass stellar misfits in the galaxy. As a joint member of the education department at the American Museum of Natural History, Faherty strives to create more opportunities for underrepresented minorities to enter STEM fields through unique outreach endeavors. Her favorite star is Eta Carina, and her favorite moon is Enceladus. And we also have her website in the link. So
I don't mean to interrupt.
yes,
But I'm pretty sure that's pronounced enchiladas. Okay.
enchiladas. I'll make a note of that. Thank you for the.
I just don't want you to be embarrassed in the
Yeah,
future.
I appreciate that.
That's okay. We'll bring it up with the IAU. That's our bad.
Jackie, do you want to share your screen?
Are we ready?
Oh, I think we're ready. I hope.
Do you think your audience is ready? Can you tell in the chat if they're ready, Kaylin? Can we just get a roll call in the chat if everybody's ready?
Yeah, I'm seeing a lot of what, and let's do this. So
Let's do this. Okay, as long as it's enough of a good thing. Okay. All right, I'm going to start sharing. And I'm going to talk for about 15 minutes is what we decided, right, Cameron? So that no one has to hear me talk for longer than that.
Yeah, plus or minus. If you go a little bit longer, I'm not going to give you the cane and pull you off camera.
You're allowed to, though. All right, here we go. So the topic that I'm going to talk about today is a citizen science project, which is called Backyard Worlds: Planet 9. Now, already the word citizen science is something I want to reflect on because it's kind of become problematic to refer to the word citizen science. Sometimes we call it people-powered research. You do not have to be a citizen to work on these projects. It's all about inviting anyone and everyone to participate in the scientific process. And the one that I co-founded back now 4 years ago, I think, is called Backyard Worlds: Planet 9. And for those that want interesting inside info, if I get a glass of kava, I'll give you some secret stuff that happened to us when we first tried to launch. We had a different name that we were not allowed to use, and there's a NASA story behind that I think Constantine might want to hear about. That's a teaser, but now we're called Backyard Worlds: Planet 9. And you can find us on Zooniverse, the Zooniverse platform of all of the different citizen science projects, but backyardworlds.org is our project. And the tagline that we have is help us scan the realm beyond Neptune for Brown Dwarfs and Planet 9. I co-founded it with several astronomers that I'll tell you about. It was co-founded specifically with a NASA astronomer. So we've got a lot of NASA support for this project. And I want to introduce some of the most important people for it before I tell you exactly what we found and what we've been doing. And so our research team, the co-founders, Mark Kushner, who's at NASA, who's currently the ambassador for citizen science for NASA, Aaron Meisner, who's now at NOAO Labs, Adam Schneider, who just joined the staff at USNO. And then we have some key collaborators, and then very, very key people around the world that have been participating with us, scanning the realm beyond Neptune for brown dwarfs and Planet 9. And I'm going to tell you how exactly we've been doing this and why Planet 9 was our tag, our like hook to get you involved. And hopefully some of you will want to be involved after you hear the cool results that we have. So important to also know is where we've been gathering people from around the world to help us. We have over 200,000 now users that have been helping us scan the realm beyond Neptune to try and find moving objects that are representative of like undiscovered, unmapped, uncharted things that astronomers that have just missed when we've been scanning the skies. Because we're looking for things that are very cold, that move very fast, and that require your eyeballs to try and find them. This is a map of where our users are. We're getting people from around the world to help us scan images, blink them, and try and find objects that may have moved. We all get together a couple times, I was gonna say a couple times a week, once a week for an hour and a half for a weekly hangout. This is a screenshot I took of it that it used to be alternate weeks of just science team, and then all the citizen scientists could come. But since COVID happened, everybody's allowed to come in. And this is a screenshot of one of our Backyard Worlds meetings. And pictured there is a citizen scientist named David Black, who's actually in high school. And he joined us from his school library, which was pretty cool. So if there's any high schoolers watching this, you can be a part of this project too. So join us on weekly hangouts. We invite everybody, even the Kaylin, Constantine, Cameron, you guys are all invited to come join in our research hangouts where you can hear about the science that we've been doing. I got a thumbs up. And here's our method. So the whole sky, 360 degrees, everywhere in every direction that you look. While you might think like, oh, we totally know everything, the closest star. And that's one to throw in for the chat right now. And it was one of my trivia questions, but something for the chat. Why don't you guys try and answer this? What do you think the closest star is? What is the closest star? And then what's the second closest? And okay, so not the sun, like the one beyond the solar system. What's the closest close star to us? Can you see it with your eye? Do you know what the answer to that is? No, you cannot see it with your eye. It's called Proxima Centauri, and you can't see it because it's too faint. You don't need much of an aid to be able to see it, but that should make you wonder, okay, so I can't see it with my eye and it's a star and it's closer than any other star. So is it possible that there's another object that's too cold to see, but it might be out there? And maybe it's closer than that closest star. Could that be? And I would scream to the rooftops, yes, absolutely. There are objects that are colder than stars and hotter than planets, and they're called brown dwarfs. They're in between. They don't have enough mass to have a core that can fuse hydrogen into helium. Instead, when they're born, they kind of form like stars, or at least we think so, and then they cool through their lives. And the thing is, they were hard to find because all their light comes in the infrared. And here, displayed here, is a screenshot of what we decided to try and do, because as good as astronomers are, we definitely aren't able to take the whole sky and figure out where everything exactly is. There's not enough astronomers, and it's too hard to scan the sky perfectly because all sorts of things can go wrong when you're scanning the sky and trying to find objects. And brown dwarfs are especially complicated because they test the limits of technology. They test the limits of what you can actually do with ground-based and even space-based things because they're faint. They give off the majority of their light in the infrared, not in the optical where your eyeball sees. And they're not that hot because they don't have a core that can fuse hydrogen into helium. So they can hide. And because they can hide, they're harder to find. So what we devised is the Backyard Worlds method, which is we took these images that NASA had produced from a survey called the Wide Field Infrared Survey Explorer mission. Scanned the entire sky and space with wavelengths that your eyeball can't see, and we subtract them. And we look to see if in that subtraction, you catch any object that has moved. So it's the infrared. So infrared objects are going to be cold objects from my perspective. And if we subtract two objects, which I should say were taken with several years in between them, they'll subtract out and you'll see an object that moves that way. So you want it to be cold and you want it to be moving. You find those two things together and you're onto something interesting. Could it be closer than the closest star? Totally, maybe. It can happen. So that's the Backyard Worlds method. Now, to hook people on this, we figured saying to everybody, okay, jump in with us, find an object, a brown dwarf, which it's already hard for me to explain to you like what it is, but I hope you're now charged up for them. But we realized like everybody wants Planet 9 as well. You're going to hear in Constantine's talk, blah, it's amazing, blah, 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 blah. And if we find it, yes. But from my perspective, there may be brown dwarfs that are just outside the solar system that we didn't see because they're too cold for us to be able to see. And our technology isn't just quite there. And in the past 4 years, right now it's actually the past 6 years, there have been 2 different objects discovered, 2 different brown dwarfs that were discovered that are in the top 5 closest objects to the sun. They went entirely missed by everyone until the year 2013 and 2014. So I guess that's 7 years ago now. Can you imagine that? And you know what? No star is entering. We're not going to find a star. That's very unlikely. That's closer in the top 5. But you will find brown dwarfs because they're cold and they can hide. But our hook for Backyard Worlds Planet 9, which is still possible, is that we could, in theory, also find Planet 9. This is our solar system, and then we have this mysterious other object that might be out there that we're not exactly sure how we're going to find it, how far away it is, and Constantine's going to tell you all about that in there. So we do have a hook. You can blink images with us that are in the infrared, and you do have the potential of discovering another planet in our solar system. However, this is what I'd really like to find. See that orange dot there? I'm going to blink the images for you. Now, that object, that running little red dot like that, that object, I think, is one of the most amazing discoveries in astronomy over my career. It was made by a guy named Kevin Lumen at Penn State using the exact method that we employ with our project Backyard Worlds Planet 9. And that is take the images and look to see if something moves and it's cold. And that orange dot that's flying across there, that was one of those 2 objects I just mentioned that is in the solar system. I'm sorry, in the solar neighborhood. It's number 4. And here's what's crazy about it. It is very cold. It is just 100 degrees warmer than Jupiter. And at any given age you could give it. So this is this problem with brown dwarfs. If you don't know the age, you don't know the mass. It's a degeneracy problem. But it doesn't really matter. No matter what age you put at it, this thing can't really be more massive than 10 times the mass of Jupiter. More likely, it's 5 or 6 times the mass of Jupiter. So you're basically staring at a free-floating world, an isolated, frozen, free-floating world sitting in our backyard. And those that worked on the mission, the WISE mission, that this Backyard Worlds program is all designed around, it was so hard to find this thing because it was sitting on a galaxy in the original image, and it just didn't pop out right. So it took somebody, Kevin Luhman, blinking thousands and thousands of images a night in order to discover it. So we designed this project, Backyard Worlds Planet 9, to find more of these. And I'll tell you a little bit about what we found. So here's a little showcase with these 200,000 users and the 50 super users that we have that work with us on Backyard Worlds. They have found a myriad of moving objects that are very close to us. Well, hopefully you can see in this montage all of these orange dots that are careening across. And I should mention they're orange because we actually subtract 2 different wavelengths of light to bring out the color of the object. And the more orange it is, the colder it is. And we want something cold, because cold and fast moving like these means that you've got a low mass thing that's probably really close by. So this is a myriad of some of the exciting ones that we found. Not only have they found them, our troop of citizen scientists have been finding these objects in bulk. They've also been finding them moving with other objects. So in this montage here, you can see more than one moving. An orange dot is moving with a dark black dot. The dark black dot is a primary star. So a K star, or a white dwarf in one of the cases, or a K and an M star, or another M star. And they're moving with a really low temperature brown dwarf that had been completely missed by scientists until our citizens took to the case and started blinking the images. Maybe they showed up for Planet 9. Maybe they showed up because they wanted to scan the realm and look for brown dwarfs. Either way, they were able to uncover these objects co-moving together. And we've been working hard with them, publishing several papers. You might have seen a couple of the results in the news. We had a really cool result recently that I'm going to end on, and I'll talk you through it with this movie. So this is a little flight from outside of the galaxy on our way in. To showcase one of our bigger results is that among our 100,000, 200,000 citizen scientists, there were 25 of them that were recently on a publication. And as we fly in here, we're going to narrow in on what's called the solar neighborhood. As we come in, I'm going to fly through a set of stars that are stars you also can't really see. These are stars that are part of what's called the Gaia DR2 catalog. A lot of stars for which we've measured their distances. Now, the only objects that I've left on here are brown dwarf discoveries that our citizen scientists have made. And that grid there, that's showing you there, that's showing you basically 60 light years away from the sun. 60 light years is what I refer to as spitting distance away from the sun. They have mapped a territory of objects, of cold objects that no one had seen before, that astronomers struggled to discover. And we're going to kind of fly around it. And once I move to a certain view, I'm going to turn on motion here so you can see them moving through the galaxy. They have very different velocities. This is their bulk motion through the galaxy. They were found through their motion. And so it's a very exciting thing for me to be able to say that these sources were, number one, helping us map the density of objects that are nearby. We want to know what the end product of star formation is. And these objects certainly give us that. And they're also objects that are giving us the information that we need when we study them in detail about objects that are like Jupiter. So this is just going to come in and give you a last view as we move through. You can see I've left them up in the sky. That's our solar system there. I'm going to come in and take us into perspective on Earth. So of the highlights, there's hundreds that are in our new paper. It got great press. It was all over the place because everybody loved the feel-good story of citizen scientists helping to map out the nearby solar neighborhood. And I encourage all of you to check out our website, backyardworlds.org. Check out our new discoveries. We write about them in our blog. Maybe join a research call and stay tuned because we have so much more to come. We have many new objects and we don't have it yet, but I really am hoping. I'm really hoping for Planet 9. Constantine, you can hope for that. I'm really hoping for an object that is within closer than Proxima Centauri. And I think it might be there. Okay. I went a minute over, Cameron.
No, you did great. That's awesome. Thank you very much, Jackie. Lots of good questions in the audience, but no, this is super cool. Citizen science stuff is great. That there are opportunities where people can participate in, research grade science that's going on. So I think that's super cool. Okay, so questions. Let's see. There were a bunch of questions about brown dwarfs. What is the closest that a big brown dwarf can be and not be ruled out for being already detected gravitationally?
The biggest that it could be and not ruled out.
Yeah, I think they mean like, I think what this is like, how big would something have to be that we would already have detected it?
So I think I'd rather answer a take on this question that I think maybe they also want to get at, which is what's the size limit of these things? Mm-hmm. And this gets me into my pet peeve in life, which is the word planet and how it gets used. And it's super exciting when it's applied to some things. And then other things, which are basically the same kind of object, are demoted. So Planet 9, for instance, Constantine, was our hook to get people in. But really, we're finding objects like your Planet 9 is really tiny. Brown dwarfs are like that 0855 object that I showed, the close one, the one that we designed the whole thing around. It's just a couple times more massive than Jupiter. It's basically a planet. It's so dumb that the word planet applied to you is all like spectacular and amazing. But I have to use the word brown dwarf, which I do love. And I don't get as much excitement. So the word.
Let me ask you this. Is it really 2 times as massive as Jupiter?
The lower bound of it, if it's just 1 billion years old, is 3 times the mass of Jupiter.
So it is a planet. I mean, the deuterium burning limit is 13 Jupiter masses, roughly speaking.
So this becomes the problem. 13 Jupiter masses doesn't work as a definition for planet because everybody debates those. Like you find them isolated. What we want to use is formation and not the deuterium burning. If all we want to do is deuterium burning versus not, then yes, sure, they're planets. But
I must disagree with this because like, I think we don't know how things form, right? I mean, just looking at a you don't know if it's an ejected planet that was ejected during an instability like the one solar system experienced early in its lifetime, or if it formed in isolation like a star, in which case it's indeed a full-fledged star. That's a piece of information that's not observable. Are
there not signatures that could be revealed? Or we just don't know. We haven't predicted any that would be able to distinguish between those two.
I will say it is a pillar of my research to determine the signatures of formation for this exact thing. So one of the things I look for is the signature within the brown dwarf data or the exoplanet data. Because I have both. I have the objects where you would be able to compare them all. I have them isolated at 5 Jupiter masses. I have them with a star close in and far away. And I've got atmospheric data on all 3. And we've been doing retrievals. We've been looking at their spectra really carefully in order to retrieve out the abundances that are in there. So we're looking for the primitive abundances that might tell us something, like the C/O ratio is the like unfortunate holy grail that can get mixed up. So how much carbon and oxygen
for our audience, carbon to oxygen.
Yeah.
So those things we're kind of looking into. And the National Science Foundation just funded us to do this exact kind of thing, to look for the smoking guns, if they exist, on them. Whether it's going to be there or not, I don't know.
Why would you expect the carbon to oxygen ratio to be different between something that's formed by itself, not in a stellar system, whereas something that's formed in a stellar system and then gets ejected, like Constantine was saying?
Well, you can't really tell the difference of ejection. Ejection is a really difficult hypothesis to take on. It's also hard to eject these objects because they're very massive. So in order to eject these objects, and Constantine, you can speak to this, you need something more massive or another event, like maybe a stellar flyby can do it. We haven't figured out a scenario where it makes sense that these are the objects that get massively ejected, because we find a lot of them. I studied the ones that are at the like 5 to 10 Jupiter mass range, that are young or that are really cold, because that's where my laser focus is in science, because I want to know what's the end product of star formation or the top end of planet formation. Where is it all come in at? And these are the exact objects that are going to help us figure it out.
Yeah, it's super exciting stuff. I mean, if you look at the current, census of extrasolar planets, I think the best example, the best case for ejection, which is, since you mentioned it, is HR 8799, right? It's a system of 4, young planets, and it appears to be, and it's distant, right? So it appears to be headed for an instability, right, on sort of 100 million year time scale, given the data that we have. And the exciting thing is, all you really need to eject stuff is that you need the escape velocity of your companions that are ejecting you to be greater than the orbital velocity. That's the criterion. So, something like HR 8799, I think, satisfies that that criteria. Now, I'm not saying that that's actually how brown dwarfs get out to where they are in large fraction. All I'm saying is that it's an interesting, question to consider. What fraction of the low mass end of star formation we observe are actually planets, right? Planets that are formed, right, in protoplanetary disks. I think a good proxy for this might be the radius, right? Planets form, we think, for the most part, by core accretion, right? So they're heavy in elements that diminishes their radius. So that, I think, might be a pretty good clue, although it's of course hard to measure that directly.
Yeah, there's a student of David Kipping's who wrote a really cool paper, which was attempting to put it all in perspective with radius and mass. The problem is you can't measure radii. For brown dwarf radii are impossible to measure. And so I have to work around that, and I do all the time, by getting to the age and then getting to the bolometric luminosity, and now I'm talking too jargony for the audience, but looking, yeah, too much, because I feel like now I'm just talking to Constantine and you guys. But
no, but this is, I mean, it's useful to have these kinds of discussions. Just try and keep the jargon out of it. That's all.
Yeah, well, the crappy crap is that we don't have the info we need. Yeah, you know what I'd like to do, Constantine? I'd like to walk right on up to it with a tape measure and measure that and stick it on a scale, and then take little dollops of these objects and then even ask it, like, who formed you? Where'd you form? Yeah. And I can't do that.
Do you ever find brown dwarfs in binary systems where you could use transit method for being able to determine the size? Because that is a typical way that exoplanets are found, right? So,
right. So this is the other complicated part of brown dwarfs. There's something called the brown dwarf desert. You don't find them close in. So transiting brown dwarf systems are fairly rare. There's only 12 of them that have ever been found. Okay. It's between 12 and maybe 15, or it might be 8. It's in this like not great number. And so we don't have that. And those aren't the greatest examples, because when they're close in, they have inflated radii. Kalen's nodding, like, you know this. You know what it is, Kalen, that we should do. And this is something that I know you're working on, because or at least you had the idea to work with Davy Kirkpatrick on this, which is what we need to do is use the technique called microlensing. And I am on this game. And for those interested, I'm about to put in a citizen science project, a new one, to look in the galactic plane where it's really crowded for more of the brown dwarfs, cold ones, where I want to measure this, because we could do this event, like the microlensing event that Kaylin knows a lot about, in order to get mass measurements for them that way, because otherwise we don't have a really good way of getting the mass, and I'm going to work around the radius a different way.
Yeah, and this dovetails really well. I'd flagged one of the questions in the chat during your talk, Jackie. It said, what is the closest, oops, no, I'm reading the one that was just read. There was one about microlensing. See if I can find it.
Yeah, the question was,
was
can you use gravitational microlensing events to detect nearby brown dwarfs?
Yeah, that's what it was. And so this is exactly what Jackie's mentioning here. And we've kind of kicked around an idea with another collaborator. So I'll get up on a little bit of a terminology kind of soapbox. So microlensing as a descriptor of a subset of lensing phenomena refers to intragalactic, so all within our Milky Way galaxy lensing. But when the angular scales are of a certain length, are very small. And that happens when you have these background objects whose light are getting amplified, are roughly in the galactic center, about 25,000 light years away. And then the lensing objects, the ones that cause the background object to get brighter, and as Jackie mentioned, the one whose masses we're able to measure, are kind of roughly halfway between. That's not a great formula for trying to measure things that are very, very close to the Earth, very close to where our telescopes and eyeballs are, and are low mass. You know, planets and brown dwarfs aren't as massive as, say, stars or very massive stars. However, that said, there are a bunch of different kind of programs and missions. The Gaia spacecraft is one of them. And then there's a project that Jackie and another collaborator are involved in to do what effectively is called mesolensing. And so this is take that same basic principle of microlensing, but change the distance scales and the angular scales that you're talking about. And you can kind of repurpose it to look at objects that are more nearby and do exactly this, try to measure masses of brown dwarfs, as well as maybe even, you know, other local, you know, Jackie was mentioning, you were talking about like stars that are nearby, but that are very faint. And so if they're faint, maybe it's hard to get some measurements of basic fundamental properties, and lensing is a way to get around that, since you don't actually care about the light from the object, you care about the mass. Yeah, so I would say stay tuned. I would say this is fairly promising.
This is totally going to be a thing at some point, if I have anything to do with astronomy in the next couple of years, because it's important. People don't realize how important it is. I also think if we went deeper in the infrared, this would be my bet, and I'll bet all of you here and all the people on YouTube Live, if we did an infrared distance parallax survey, distance survey, a deep infrared one, you would find free-floating Jupiters and free-floating isolated objects like these everywhere. They'd freaking be everywhere. And you know what? Everybody would want to be studying them then, because because JWST is coming on, and the James Webb Space Telescope, this, you know, big beast of a telescope that's going 1 million miles away, but is going to be studying the sky in infrared light. And the main targets, some of the main GTO targets, as like, oh, how's this thing going to work? They turn to our cold brown dwarfs because they are freaking Jupiter. We study Jupiter. I study clouds. I study the way the clouds move. I study the variability. I look for aurora. We look for the signatures of planets through the aurora that happen on these objects.
We see aurora on brown dwarfs?
Hell yeah, you do. And we've seen some of the strongest magnetic fields that you can get. We've measured the wind speed on a brown dwarf. Can you say that about an exoplanet? No. You can do it on the brown dwarf.
Whoa. We don't have to.
We can.
It doesn't have to turn
I'm
into
sorry.
a
I'm
wall.
sorry. I'm sorry. We've done it for Jupiter. We've done it for the, you know, solar system planets.
Wait, but
One-eyed
for aurora,
he's got 2 km/s winds. I'm saying. I'm just
for aurora. I mean, the aurora in the solar system are all caused because the magnetic field, like the solar wind from coming from the sun, hits the magnetic fields of the individual planets. But for a brown dwarf, you were saying there were only a handful of brown dwarfs that were in systems with other stars.
Yeah, right. This
are they
is
getting magnetic fields from the galaxy, or like like cosmic rays that are hitting it from other like distant stars, and then that's coming down along the magnetic poles?
Well, so there's two different ideas in where they get the aurora from on the brown dwarf, which is it's an isolated system from the brown dwarf's surroundings and its own atmosphere or in this magnetic field. The other thing is, remember why Jupiter has its aurora?
Oh, because
it's like pop quiz, because of Io.
Yeah.
So you want to find an exoplanet around a brown dwarf or a planet? This is the other theory. You see the aurora, follow the aurora, and that's giving you an indication, because there's no reason why you find a brown dwarf that's like 5 times the mass of Jupiter. What does Jupiter have? It has freaking 60 something moons. Okay, great. We're going to find the same damn thing around all of our brown dwarfs. And it's way easier to study them than find Jupiter and then find its moons. So whatever, call them moons or call them planets around the brown dwarf. But
this was one of the questions in the chat was, if you find something orbiting around a brown dwarf, is it a moon or is it a planet?
So unfortunately, we have this terrible way of referring to them. And it gets called planetary mass companions sometimes, PMCOs, or planemos. And it's kind of like the half-ass way, like of getting around the idea. What was that? What did you call it?
Geronimos, yeah. I feel like Geronimo is just a good term for anything, really.
Well, so I have, when I go on my high horse, I just think everybody should call everything worlds and stop using the word planet. It causes too much of an emotional problem and too much of like a jargony nomenclature problem among astronomers. This whole deuterium burning boundary at 13 Jupiter masses thing versus like formation, we can't tell anything right now. So they're all worlds. We're done with calling anything.
Would you get on board? So one of my, major initiatives that really hasn't taken off quite yet is, instead of the term free floating planet, so gravity, it's an R² law. It doesn't go to 0 in the universe. So nothing's free floating. And especially for a lot of these free floating planets, we know that they're planetary mass-ish. So what
that'd be a bad pun. I already know this.
No, it's well, maybe. Solivity, planetary mass object, or a SPLAMO. I think that we should be rebranding these, because free floating planet is wrong, on at least 2 physical axes.
So, Kaylin, though, it sounds like you have been talking to Davy Kirkpatrick, who we've been mentioning far too much. And I should say Davy, who we've now mentioned more than once, is my academic grandfather. He's also like the father of brown dwarfs. He was the PhD advisor for my PhD advisor. And he's a collaborator of Kaylin's now, and he loves to use the word, I don't even know how to say it right, salivinigan.
Yeah, it's an old word that means wanderer. So, it's
right.
Linguistic kind of flair to it. And I'm kind of appending to that, planetary mass, kind of to dovetail with what you're saying.
SPLAMO.
SPLAMO, where I'm really going with this is SPLAMO. You heard it here first.
You should make some stickers.
Yeah.
Yeah.
The only objection to this, like, literally, is that I feel like, I'm just so sad I didn't come up with that.
You can take a vote.
Sounds like either a kids show or like a rock band that was in the 80s, like Wham.
Season, but
Wham. Good one.
I like
the
it.
SPLAMO. Yeah.
With an exclamation point at the end. That's what.
So Jackie, I have a question to kind of bring everything back full circle. So do this big, infrared survey. There's going to be these Jupiter mass SPLAMOs everywhere, and to go back to what you were saying earlier. So would most of these have formed isolated, or would most of these have been ejected? What would your second claim be?
I would say most of them form isolated, because what we've been doing is counting them. Like, that's part of what Backyard Worlds has allowed us to do, because you want to look at the numbers in a volume limited sample. So you want to like say, tell me everything that's in 60 light years. I'm going to count them all up, and I'm going to see if it progresses the way I would think star formation will start to trail off. And so for a while, it was like, okay, how many are there going to be? I'm not sure. And when the WISE mission first released their results, they said, well, before they released it, when they started the survey, they said, look, there's going to be 1 to maybe 5 brown dwarfs for every star. It's just the way it's the way the distribution of things are going to look. We think that it probably gets more efficient towards the end. This is what we think. But then the results came in, and we looked at the limited area of the volume, and it's maybe 1 brown dwarf for every 6 stars. It went the other way. Mm-hmm. And so you see it trail down. However, this is my however on here, why I think the ejected planet, or the, it's got to be ejected, or it forms and then something happens. Like, it's a disturbed system. Breaks up, it dynamically evolves. I don't like ejection. It feels like a wrong word. It's like the Gwyneth Paltrow thing of like, what did she say? Conscious decoupling. Yeah. Like when the brown dwarf and its host just decide to go their separate ways. Yeah. Not ejected. Right. Just because, well, I mean, that in that theory, it's like a giant molecular cloud, interactions and all of that, because that happens to binary systems. But when this object 0855, the cold frickin' one that's sitting out there, was discovered at just 8 light years away, I basically changed my mind on everything. And it was one data point, but it was one that makes me so unbelievably uncomfortable. Why is that so close to us? We didn't even think it was going to exist. We got convinced it didn't after the first WISE result came out, when we saw the mass function go down. And we're like, no, it's 1 star for every brown dwarf. It gets really inefficient at the end. You're not going to find any of those cold ones. There's no way they're around. Oh, but not only is one around, it's the 4th freaking closest one to the sun. And you can't find them when they're much farther away because they're too faint. They're at the limit of our technology. So if we opened our eyes a bit more to the infrared, this is why I'm saying I think sky would light up like a Christmas tree with some of these things.
So
I stand by that.
Would the Roman Space Telescope be a good tool to use with wide? So this future flagship mission that has a wide field camera, so it covers a relatively large area in the sky, 2 square degrees for people out there, and it's looking about 2 microns, so in the near infrared.
Oh, it goes that far into IR? It does H-band or K-band?
Yeah. I think it currently cuts off right at 2.
Okay.
So it's solidly
H-band.
So the
transmission curve.
The problem we have, that one's going to be great for a certain thing. And I should mention that the 4th closest one to the sun is the one I kept focusing on because it's really cold. It's 100 degrees Kelvin warmer than Jupiter. But there's another one that was also found that was completely missed. And it's the 3rd closest object to the sun. It's called, and this was the trivia. I shouldn't say it, Kaylin, but
I think you can say it because I don't think the question got included in the overall.
Yeah, I don't know if I actually saw.
Okay.
I think it's
let her rip.
Okay, so it's called Lumen 16. It's named after the same guy that found 0855. It's the 16th. It's the 16th binary system. There's 2 of them. There's not just one. That's 2. Here's what's crazy, right? Brown dwarfs were theorized in the 1950s. And then people started searching, just like we do in anything in astronomy. Planet 9 search is going on. Like, everybody looks, you get all your telescope time, you go freaking, batshit crazy trying to find the thing. Because as soon as you do, it's going to splash on the news, it's going to splash everywhere, and the science will explode because who knows, it's going to be a mystery, right? But so the 60s, the 70s, the 80s go by, nothing, no brown dwarfs. There's a couple of candidates, but they're all wrong. Nothing. Mid 90s, 1995. Actually the exact same year, that the first exoplanet around a sun-like star was found, 51 Peg B, the first bona fide brown dwarf is discovered. Splashes everywhere, news, headlines, crowd go wild, right? And this is the thing, though. This is what's freaking insane. So that object, which is called Gliese 229b, it's got methane in its atmosphere. It's like, no way is that a star. I've got our first bona fide brown dwarfs. After that, floodgates open, lots of brown dwarfs discovered, hundreds, thousands now, you know, blah, blah, blah. But 2013, Kevin Luhman, doing the same searching, the same backyard worlds method, he discovers a brown dwarf that is bona fide brown dwarf sitting there at 6 light years away. And if you go back, it was on all the old photographic plates. Everybody missed it. The reason they missed it is because it's in a crowded area of the sky, and nobody could find anything in the crowded area of the sky. Couldn't find jack shit, which is also why we have to use this kind of method of blinking and using a lot of eyes. Because if you freaking missed it, all of brown dwarf science would have been different. It should have been discovered in the 70s, because that's the first time we can trace back where it's on an image. And it's got its motion is a quarter of the full moon over a century. So it will cross the full moon in 400 years, which is actually freaking fast. It's in like the top 20 fastest objects that move. So you should be able to find it. But many people searched like crazy. I'm not like, these searches were crazy, and it was missed completely until Kevin Luhman came and just diligently with the WISE data just looked and looked and looked, and then he found it. And it was like, are you kidding me? All brown dwarf scientists, all of us did the same thing at the same time. We were like, holy shit.
Well, and that crowding is exactly what makes it, or what has made it historically difficult to do lensing searches like this, because you're kind of playing a numbers game. You're rolling the dice and saying, you know, am I going to see the brightening of some object due to some massive intervening object, you know, like a local brown dwarf or something. To win the numbers game, you have to look in places where it's very crowded, as you're saying. And that's been very hard, especially at redder, you know, infrared wavelengths to do, and not just get swamped by, you know, a high density of stars. But the game is changing, you know, with James Webb and the Roman, as you said.
Yeah. There's good stuff. Maybe even Planet 9 is sitting there in the crowded area.
That's
well, I mean,
right.
Constantine's going to tell us where it is, but
Yeah.
What was that?
Like I said early on, and it's right there.
Okay. There are still some awesome questions, but we've taken a lot of time for this, so we have to move on so we don't keep people up, including you, Jackie, who it's already 11:30 for you.
I know.
But that was an awesome talk. Thank you very much. Excellent work. Okay.
I like that you can applaud yourself on here.
Does it show up in the YouTube? I don't know if it shows up on YouTube that you're showing little applause icons.
That's a shame.
I hope it shows up. Anyway, thank you, Jackie. We'll bring you back during our pub trivia, but for now, I'll let Kaylin introduce Constantine, and then Constantine will speak.
All right. Thank you, everybody, for staying tuned to the second half of our 3-half program. It is my extreme pleasure to introduce Professor Dr. Constantine Batygin. So, and I didn't write this. I just want you to know that Constantine wrote this first thing I'm going to say. Forbes named Professor Constantine Batygin the next physics rock star in its 2015 list of 30 under 30 young scientists who are changing the world. He received his bachelor's degree in physics from the University of California, Santa Cruz, 2008, before pursuing graduate studies at Caltech. To date, Batygin, that's him, has authored over 80 scientific publications, 80, and his research has been featured on the front cover of Scientific American. That's when you know you've made it. Prior to joining the faculty at Caltech in 2014, Batygin was a postdoc scholar at Observatoire, I believe I'm pronouncing that correct, in Côte d'Azur in Nice, France, and Harvard University. When not doing science, he moonlights as the singer of the rock band The Seventh Season. I will note too that a little known fact is that once during a live electric set in Michigan, the wiring of Konstantine's vocal mic, so he's the guitarist, singer, and overall heroic frontman of Seventh Season, was wired such that our very own Professor Batigan got shocked every few minutes as he sang, and nevertheless, he soldiered on, undaunted. And I will close by saying as well that his fame, I presume primarily due to Seventh Season, also landed him an interview spot with the extremely popular Russian, should I say influencer? I'll say celebrity. Probably shouldn't say Russian influencer. Andrei Kunyaev, am I pronouncing that right? Who's the co-host of the Kuji podcast, a video that now has over 7 million views on YouTube. So if you speak Russian and you would like to follow in the wake of Professor Batigan's fame, I encourage you to look that up. So thanks, Konstantin, for agreeing to give a talk, and take it away.
Yeah, wow, Kaylin. Thank you for that. Thank you for that intro. And you're absolutely right that I was on a Forbes list, but it was the wrong list. I was hoping to, and still in fact hoping to end up on like the rich list one day, but well, we'll see. They put me on a different list. Okay, so look, Jackie in her wonderful talk mentioned Planet 9 multiple times, which was great. But I think it is time we address why we think there is a Planet 9 in the solar system and what we are doing, both on the observational front, but perhaps more importantly at this time on the theoretical front, to understand its properties and to really zoom in on what we think its orbit might look like. So let me begin here by kind of taking you back a couple decades and pointing out that as far back as 1990, right, when 30 years ago, we thought that Pluto was the end of the solar system. And what you're seeing here is the sort of a top-down view with the pink ellipses being Jupiter, Saturn, Uranus, Neptune. The blue one is Pluto. That was what we thought was the edge of the outer solar system. We now understand that it's not the edge, and Pluto is nothing more than a particularly massive object, which is part of a whole population of bodies collectively known as the Kuiper Belt, which you're seeing here a subset of. And these are objects for which we know the orbits really well. So what I'm really getting at here is that there is a second asteroid belt, if you will, that lies beyond the orbit of Neptune. A lot of people know about the usual asteroid belt that's called the asteroid belt that lies beyond the orbits of Mars and Jupiter. This is a second, more vast population of minor bodies that resides beyond Neptune. Why is it there? Okay, that's a really, really good question that immediately actually overturned our whole understanding of how the early solar system formed and evolved. So here is an animation. I'm taking you back now 4.5 billion years. This is an animation of what the solar system did in its very early evolution, basically immediately after it came out of the cloud of gas and dust that formed the planets. And the planets used to be in a much more compact configuration, surrounded by a much more extensive field of icy debris. And as dynamical evolution unfolded, much of this debris was ejected out into the cosmos as the planets underwent a transient phase of dynamical instability. You kind of see this here. You see the planets dancing around quite a bit and their orbits expanding. This is not just an animation. It looks beautiful. It was done at the California Academy of Sciences, but it's not just an animation. This is actually the result of a numerical calculation that we did back maybe 8 or so years ago. So the solar system, as I said, started out with all of this icy debris, about 20 Earth masses of icy debris, which got ejected, but some of it stayed behind. That material that stayed behind is what we now see as the Kuiper belt. And that's the population of stuff, if you will, that lives beyond Neptune. Something that we noticed back in 2016, when we were inspired by a paper written by our colleagues, Chad Trujillo and Scott Shepard, my partner in crime, Mike Brown, and I were kind of looking at the data, and something we noticed that was profound is that if you look at the most distant orbits that we know of in the Kuiper belt, they all appear to point into the same direction. As you can see, perhaps on your screens, all of them point to the left. And if you turn them around, all of them sort of lie in the same planes, as if you can put a piece of paper through this population of orbits, and it would be inclined with respect to the plane of the solar system by about 20 degrees. Now, this was the data as of 2016. It has been 4 years since then, in case you haven't noticed. And the data set has basically doubled since then. Although this clustering is certainly imperfect, it remains very much there, especially among orbits in the distant Kuiper belt that are stable. Okay? Objects which are not being flung around by Neptune rapidly. We can ask the question of, what are the chances that we would end up with a distant solar system that looks like this just from, statistical grounds, right? Like, what are the chances that we're seeing this by accident? And the chances are less than 0.2%. Okay, so less than 1 chance in 500 that we're seeing this by accident or by some observational bias or anything like that. So it appears that this signal, the fact that if you go well beyond Neptune, and Neptune here is shown as this closest in circle, the outer circle is 250 times the distance between the Earth and the Sun, about almost 10 times the orbital distance of Neptune. So these are really, really distant objects. Okay, and it appears that they're all clustered together. What happens if we take this solar system as we see it today and just let it go and say, okay, well, go ahead and evolve? The answer is, in a few 100 million years, the orbits will disperse. Okay, they will become randomized. Okay, so really, not only is it peculiar that orbits like these appear aligned, it's that if you allow this configuration to evolve, it will change. This alignment, if you will, this clustering of orbits is unstable. So what does this mean? This means that something else is out there holding these orbits together, keeping them confined. What is that something? Well, back in 2016, we proposed that this object is a planetary mass companion, as we heard from Jackie, but a much less massive one than brown dwarfs. Okay, this is what we think perhaps a super Earth type planet, which is out in the distant solar system, maintaining the confinement of these objects. How do we know that it can do this? Well, what you're seeing here on your screens right now is an outcome of a numerical calculation that we did, a computer simulation of the long-term evolution of the solar system, if you will, where we begin with the Kuiper belt, okay, this population of debris beyond Neptune in a completely randomized state, and we allow it to evolve over the lifetime of the solar system, subject to both gravitational perturbations of the usual giant planets, that's Jupiter, Saturn, Uranus, and Neptune. You can actually see the orbits of Uranus and Neptune here as pink little circles right there, as well as the orbital influence of planet 9, which you see as this big ellipse. And if you basically watch this movie long enough, it takes a couple billion years for the effect to really kick in. But right about now, you are starting to see that the orbits that are surviving are the ones that are pointing in the opposite direction from that of the major axis of planet 9's orbit. I do really hope that at least many of you agree that this is happening. Because if this is not happening, right, if it's not true, then the whole thing is wrong, okay? But I think it is actually true that the surviving orbits are the ones pointing into the opposite direction from Planet Nine's orbit, okay? Now, it's been, as I of course mentioned, a few years since the original proposal of Planet Nine. And back in 2018 and 19, we took this updated data set and we did a really thorough numerical exploration. By that, I mean running thousands of these computational models on a supercomputer, really getting into the nitty-gritty of how this confinement works, how Planet Nine's gravitational effects act to affect the orbits that we see together. And what we realized back last year in an article published in 2019 is that in the original paper, we got things wrong by sort of a factor of 2. Now, this is astronomy, okay? Getting things wrong by a factor of 2 is otherwise known as getting things wrong by a factor of 1, okay? It's the first rule of astronomy, is that 2 is also equal to 1. But what we understood is that if our models are right, then Planet Nine, right, is actually less massive than we thought originally. We originally thought it was about 10 Earth masses. We now think it's about 5, okay, closer to what a typical extrasolar planet looks like. Its orbital period is probably about 10,000 years instead of 20,000, which we computed back in 2016. Its orbital eccentricity is about 0.25 instead of the 0.6 we assumed back then, and so on, okay? So we got really excited by these results. Why? Because this somewhat closer in, albeit less massive planet is actually easier to detect, okay? So compared to what we thought back 4 years ago, we got real excited because we thought, man, this is gonna be brighter, bringing it closer sort of into the modern realm of what's available technologically on the largest telescopes such as Subaru, okay? So ideally, this is where I would have liked to end the talk. Unfortunately, okay, this is not how science works, right? When the moment you publish something and you think, okay, I've made this advance, the right thing to do is to go back to the beginning and to think real hard. Is there something that we could have missed, right? Is there something in our models that we aren't accounting for? So this brings me to research which is really unpublished, and I've been writing the paper. I started writing the paper yesterday, wrote a little bit more of it today. But this brings me to this picture, which is that all of those models that I showed you assume that the solar system evolves as an isolated object, right? The sun, surrounded by its planets, surrounded by its Kuiper belt objects, is a thing, and that's the universe as far as the computer that's doing the calculation is concerned. Of course, that's not true. That's not actually how the sun formed. In fact, I would go as far as to say the vast majority of stars, and this applies very much so to sun-like stars, do not form in isolation. They form in clusters. And this is a picture of the Orion Nebular Cluster, which cumulatively has about 1,000 solar masses worth of material. So you see that the sun actually had neighbors early on. And this begs the question, are we doing okay by not accounting for the effects that the solar neighborhood had on the solar system very early on? Why does it matter? Well, it matters for the following reason. Early on, when the solar system is forming, the giant planets are still accreting their mass. There's a whole bunch of debris out there which gets scattered out as the planets are still growing. Provided the sun still resides in the birth cluster in which it was born, the action of passing stars, shown here in the second panel of this little diagram, can actually circularize these objects, thereby creating what we call an inner Oort cloud, okay? A population of almost spherical population of debris that's hanging out at about a few thousand astronomical units. In other words, few thousand times the distance between the Earth and the Sun. If Planet 9 was not there, that material would just sit there and not do anything. But as we found out, the presence of Planet 9 can re-inject some of that material back into the solar system. Now, we can ask the question, does that stuff, not the stuff that's coming from the inside out, but the stuff that's coming from the outside in, does that material cluster? And it does, but more weakly than the material from that is seen in those conventional calculations that I showed you earlier. This is a bit maybe of a more getting technical, but this is a distribution. The probability density function is a function of the kind of orientation of the orbits, comparing what we get when we just calculate the material that has been ejected from the inner solar system in the black curve, and the material that is injected in from the outside in these multicolored curves. And as you can see, the multicolored curves are much more all over the place, much more dirty, if you will, than the kind of conventional standard model that we've been working with. What does this all mean? This means that if icy bodies are injected into the Kuiper belt from the Oort cloud, we need a more eccentric Planet 9 to explain the data. The downside is that a more eccentric Planet 9 also has to be further away. And I will just end with this quote that I found in a MIT Tech Review article, which I think is a really, it kind of provides a good description for why 4 years in, we still haven't found it observationally. And that, given the level of detail, it's easy to imagine that Batygin and co. can point to an area of sky and say, look there. Not so. Finding it is likely to require a dedicated survey using some of the world's biggest telescope. And we have been conducting such a survey, but turns out, observations are really, really hard. You have to stay up all night. Things go wrong all the time. There's clouds in the way. As a theorist, I'd never appreciated that until a few years ago when we started observing together with Mike. And I would say that we are about, a good 25 to 40% through the search, but there's still a ton of sky to go. My hope is that by the end of this decade, we will be back to a 9-planet solar system. All right, I'll stop here.
Great, thank you, Konstantin. That was a great talk.
Yeah, thanks, Konstantin.
Your closing thoughts, which I thought were really nice, especially the theorist turned observer perspective on things. And you actually answered one of the questions from the thread. So somebody had said, 3 years ago at Caltech, you told me your estimate was about 3 years to find it. Mike told me about 10 years last year. What's your most recent estimate to find it? And so you're saying by the end of this decade, cold fusion is 10 more years away.
It's a great question. So 3 years ago, I was almost certainly drinking, and like even more so than I am now. Look, these things, as I have found out myself, are really, really hard to predict. Example, we get time on the Subaru telescope, we go up there, right? We go to Hawaii, right? We get ready for observing night. We drive up to the telescope. There's 200-mile-an-hour wind, and the telescope is frozen shut due to hail, right? We take an ice pick and try to get into the dome and can't, right? This happened, a couple of years ago.
Right. What the hail is going on?
Well, after my own thoughts.
You're not looking for those icy bodies. Too local and they're too small.
That's right. Oh man, I have missed your puns, my friend. I have missed. This has been the worst thing about COVID, is not having your puns readily available.
No, too much. It's too much. Some of the Astronomy on Taps, he'll go up with index cards of like 12 puns that he reads like a stand-up comedian. I'm like, dude, no, you can't do
Yeah,
that.
it's great. Now I have 3 screens of that. It's just, my mind is a fountain, cascading rivulets of thought and wordplay. It's beautiful.
That it is. Yeah, my mind is a fountain is a great name for like an album that you could put out, you know.
Or the 7th season. Perhaps that can be your next album.
Yeah, that one, no royalties necessary.
Yeah, but like, I mean, so I've come to appreciate how precious every data point really is. There's a reason why, look, I mean, there's a reason why in like 4 years we've collectively, you know, all of astronomy has found like 6 Kuiper belt objects beyond, you know, 250, that with orbital periods beyond 250 AU. It is really, really hard to find them. They're really, really faint, and things have to go right night after night. That's the key thing, is that just because you have one good night of data doesn't mean you found anything. You need that parallactic motion. So we've been chugging away, doing the best we can. The good news is that the Vera Rubin telescope is coming online soon, hopefully. And that's going to be a game changer in this field. I mean, that's really going to change the landscape of the data set. My hope is that it'll just directly detect Planet 9, which would be cool, so that we can be done with this part of the problem, which is just finding it, and open up this beautiful, you know, new realm of 1,000 new problems, which is, you know, how did it get there? What does it look like? What is its atmospheric spectrum, right? I mean, just there's an infinite number of really interesting things we could ask Planet 9 the moment we find it. And I'm really excited for that moment.
One of the cool things I've taken away from both your and Jackie's talk is that Planet 9 sounds as though it's going to be sentient, and we can just ask it questions. I'm really excited about that.
I'm already asking it questions, and it answers. Yeah, that, you know, you mentioned how I got electrocuted a bunch of times. And, you know, while being electrocuted in Ypsilanti, Michigan, I heard the answers. Okay? They're not pretty.
That's funny. So somebody put a question in for Jackie's talk and then put it in again. And I had flagged it already. So, you know, Constantine, curious to hear your thoughts, but Jackie, this question is really for both of you. So just as Neptune was ultimately discovered because Uranus was not where it mathematically should have been, is it possible that Planet 9 is not where we're expecting it because of an unseen Planet 10? Or, as the people in the chat are hypothesizing, you know, is it turtles all the way down at that point if you go 9 to 9 plus 1 to 9 plus 2?
Well, so it's actually you know, it's actually a great question. You know, which is I think one other way to ask it is, you know, are there multiple bodies, in which case is that one avenue for uncertainty, right? Is that one way that you could get everything wrong, basically, by not accounting for the gravitational influence of multiple bodies? That's certainly true. It is a, you know, I would say, you know, you have to exercise caution here, because you should only make your theoretical model as complicated as the data allow it to be. Right now, there's no evidence to suggest that there's more than a single body. Moreover, as far as, you know, the dynamics really of Planet 9 and company are concerned, it's difficult to put some, like, unless you're somehow engineering the solar system, it's difficult to imagine that something that is eccentric and very far away would not scatter and clear its neighborhood when it comes to having companions. So there are avenues in which you could pursue this line of reasoning, but I don't think that it would pass, you know, the Occam's razor test.
Well, Kay, I'll just say, you know, and I mean this as a compliment, you are somewhat eccentric, and currently you're very far away. And when you come back, the neighborhood will be intact. We're eagerly awaiting you. Will not stutter.
Yeah. Well, I guess all I have to say is we'll see.
yeah. I guess I can't promise. You know. Yeah. There was another. Oh yeah. This is another dynamics kind of related question. could there be, I'm rephrasing it a little bit, could there be clues imprinted on the orbital characteristics or frequency of long period comets? Another handle that could grab onto?
Right. I mean, that's a fantastic question. I mean, look, that is actually something that we look at, and particularly we'll look at the high inclination bodies. I mean, the greatest things about comets is they come in from, not exactly everywhere, but they come in from a broader range of orbital parameter space than just conventional Kuiper belt objects. And we have looked carefully at, what does Planet 9 do to a population of highly inclined off the plane bodies. I haven't shown this in my talk, but actually this is one of the lines of evidence for the existence of Planet 9. Planet 9 takes very distant Kuiper belt objects, things that are sort of in the plane of the solar system, and flips them. Okay, and as it flips them, their eccentricities, their ellipticities go up, and they get injected into the solar system. And we see a signature of this, where we see this sort of asymmetric injection of what we call centaurs, the objects with their closest approach to the sun being somewhere in the interplanetary space. And it matches up the Planet 9 model pretty well. And we indeed use that as a constraint. And we have used that as a constraint in this paper I mentioned to, zero in on what we think the properties of Planet 9 might look like.
Wait, so
those could be
if Planet 9 is on its orbit and it is very eccentric, as you were describing, so it has this really elongated elliptical orbit, wouldn't we preferentially see a lot more comets coming from being perturbed by it in its outer orbit? So we'll get a lot more comets coming in from that direction. And do we see that in the distribution of comets that come into the solar system, that there's some sort of asymmetry where they tend to be coming from out here instead of just kind of uniformly?
So an effect that overwhelms that kind of direct perturbation that you're thinking of is actually the phase averaged potential of Planet 9. This is something that,
because it's like, it's not just this, it's actually,
it's actually the whole orbit, if you will, because look, out there things move so slowly, right? And distances get real vast. This is, I mean, it's kind of a profound point, and we didn't anticipate this back 4 years ago. Like, it took a little bit of thinking to realize this, but all of the gravitational stuff that Planet 9 does, it does due to the shape of its orbit. You could replace Planet 9 with a ring of mass that traced its orbit and it would have exactly the same effect to leading order.
Really?
Okay? Yeah. So that effect that I was talking about, the flipping of the comet, of the centaur orbits and injection, actually, it does come from a preferential direction, but that direction is about 70 degrees off the major axis of the planetary orbit. It's not really where the planet spends most of its time.
I see.
Right? It's as if those objects sample the planet at all of its
stations. Yeah. So it's like a probability distribution function for the planet in its orbit.
Precisely.
Affecting. I see. Okay.
And this comes back to one of the things Jackie was saying, and probably a good reminder for the audience at home, if we go back and remember Kepler's laws. So if something is orbiting the sun in a circle, it's going to spend equal times at all points in the circle. But if something has a very, what we're calling eccentric or elliptical orbit, it's going to spend, vastly more time at the points of its orbit that are very far from the sun. And so, from a dynamics perspective, Konstantin is saying, well, you can effectively treat it out as though the mass were smeared along that elliptical orbit. But from an observational perspective, it's going to spend more time in more distant locations. And so it's this kind of, along those two axes, thinking about it in that way.
Konstantin, could you tell the difference, or have you looked at the influence of stellar flybys? Like, do you take that into account? And what?
No, I do now. I mean, like literally, like in the conventional models, we didn't, because and by conventional models, I mean like things published up until last year, we didn't, because most of the data was at a few hundred AU, okay, a few hundred times the distance of the solar between the Earth and the Sun. At those length scales, stellar flybys don't matter. But recently, the data has grown, and there are objects now with semi-major axes in excess of 1,000 astronomical units. That was actually the motivation for us to say, okay, wait a minute, we should be thinking also about the way that Planet 9 talks to the galaxy and the way that the galaxy talks to Planet 9, mixing in material from the Oort cloud into the Kuiper belt. So look, that's very much an ongoing calculation. That's something that's coming. We'll publish soon. Yeah.
So I'm curious if you went and revisited, or what the influence was of, so in 1 million years, we're going to have a flyby by a K-dwarf, a third the mass of our own sun, Gliese 710, and it's going to come within the Oort cloud. What's the radius of influence there? And then 70,000 years ago, we had Schultz's star flyby, which, by the way, flew by with a brown dwarf. A little brown dwarf was moving with it. And that's a little M dwarf, but it flew by, right. And it was also within solar system territory. So do they really not impact enough? It seems like couldn't it just like radiate like a wave and get into the inner solar system at some level?
Well, so, I mean, the timescales for those impacts, for those particular flybys, are both too short, and the flybys that you're talking about are too far away. I mean, Gliese 710, I think the flyby is something like 70,000 AU, right? If I remember correctly.
I think it's Schultz's star, I feel like, was 70,000, but maybe I've got it reversed. Gliese 710 is going to come closer, yeah.
Right. So those length scales are basically too big. I mean, I'm sure they trigger some comet showers or something like that, which, I mean, I'm sure you could trace back some effect on it that's observable, but not really in this problem. Okay, so in the Planet 9 calculations, right, orbital timescale, like timescales for Planet 9 to really affect orbits and, raise or lower their perihelia is, 100 million years. Over those timescales, all the flybys add together like noise. So they don't average out, but they drive the orbits in a stochastic manner. So that's something we have to account for, but it's not the individual flybys that we care about. We don't care that Schultz's star flew by or Gliese 710. We care about the statistical forcing of the outer solar system by passing stars.
What if it was an O star, though? Like, what if it was a really big star? Does that change it?
So we account for that possibility. I mean, we do multiple runs, right, of every model, generating, encounters from the initial mass function. So we account for that possibility. It's not just like, here come a bunch of sun-like stars and we're ignoring everything else. We're doing the best we can to simulate the solar neighborhood and do as honest job as we can of understanding what that extrinsic forcing looks like.
But we don't have a lot of supermassive like O stars that are zooming past the solar system, right?
It's just when Gaia DR2 data came out, one of the major results that I think was the stellar flyby rate is insane. It's super high. And I did tracebacks, and there was an O star that showed up. It was bad data in Gaia DR2, but it showed up and I got freaked out because I was like, how the heck could this have happened? And it didn't, completely disrupt the solar system, but it was bad data. So it wasn't real.
I see. But it raised the question of what if a supermassive like star came past? What impact could it have on the solar system and potentially mimic Planet 9 stuff or something?
Yeah, I mean, with this stuff, it's not just it's it's amazing, but mass matters so much less than distance, right? For these types of interactions, it's all about how close you come in. An analogy that I maybe it's not an exact analogy, but I think a good way to think about it is an ideal gas, right? In an ideal gas, you care mostly about what molecule do you collide with, not, what is the most massive molecule that you saw, a mile away. And I think that here it's the same thing. Just because there are massive stars out there doesn't really do anything. It doesn't do anything for the solar system for the most part. It's what's the closest encounter. And for that, I think we have a pretty good understanding of how that works.
This is super interesting discussion, and there's a bunch of good questions that are still in the chat thread. So I don't know if y'all are looking at that. I think we should probably get going on the.
We should roll into pub trivia. People are getting a little angsty.
I'll note a couple of things.
But also, great talk, Konstantin. That was super awesome.
Yeah, another round of applause. And thanks again, Jackie. Both of these talks are great. Round of applause for both of you together. It's nice in talking about all, the orbits of these KBOs that, I feel like a lot of solar system science is usually focused on terrestrial planets. So it's really nice that they can be the center of attention.
Oh, geez, you and your puns. Dude.
I didn't even know this was. There's, Caleb, there's something called the Punderdome. Did you think of entering? It's a competition that you.
I would like to allow everybody else to save face. I feel like.
It's fair.
Yeah. There's another one I couldn't quite squeeze in, but I was going to make an orthogonal joke, but couldn't come up with it quite good.
There's nothing orthogonal in all of this.
All right, so Jackie and Kay, if you guys could stay on, stay unmuted, keep your videos on if you're down to join for the pub trivia. Sometimes we have a little bit of technical difficulty, so let's see if this just goes ahead and works. I'm gonna share screen, and what I should be sharing is a PowerPoint slide deck. Yes,
so far.
Okay.
Good.
People see this? All right, let's see if this
looks very good.
For those watching at home, I know that there are many people new to the program tonight. So the way that the infamous third half of our Astronomy on Tap works is we try to emulate the pub trivia paradigm. And so, you've got your browser up with the YouTube live channel. If you bring up another tab or another browser window and go to this URL that's listed, so POLEV, it's short for Poll Everywhere, POLLEV.com, and then /AOTLA. This is for Astronomy on Tap LA. And we'll give people kind of a few seconds to get that up and running. And what you'll see is once I launch the first question, it should just be kind of a blank-ish portal right now. But at this pollev.com /AOTLA, as we cycle through our 10 trivia questions, this will give you a chance to actually write in your answers, and then we'll be able to do a live tracking of the results, and then we'll talk about the answer to each question and science that comes up. Okay, let's see if it's going to work this time. So I will activate the first question. So do people see this question? And then on the actual slideshow.
Looks good so far.
Do you see answers coming in?
Let's see, do I? Well, you just asked it and there's a delay, so.
Oh yeah, right.
Yeah, but I'll go to the website.
So yeah, so question one is the two stars at the end of the Dipper portion of the Big Dipper are called the pointer stars. To what do they point? We've got 4 choices. And do you guys see answers coming in on the bar graph?
I don't see it. And also, is that pronounced Dipper or diaper? I always pronounce it Big Diaper.
No, answers aren't coming in yet, Kalen.
Oh, okay, I see them.
Do you need to tweak things?
Here, give me 2 minutes. I think I can fix it.
Okay.
So yeah,
I'll entertain, I'll dance. I'm an excellent dancer.
That's actually true, can confirm.
Jackie, I like your background. What's going on there?
This is from a planetarium presentation I did, and
At the
all of the
museum?
stars are in their Gaia positions, three-dimensional, and they're colored by their chemistry, by how much iron they have.
Oh, really? Wait, so the
And
very
can you
green
see?
stuff is iron, or what's going on?
Yeah, it means it's iron rich, and the purplish is when they're iron poor.
Ah, okay.
And can you see a little signature in here?
Yeah, is that the plane of the Milky Way that's high in iron?
No, this is actually an observational signature too, I should say. You should see all the circles back here are the plates, the spectroscopic plates they used with apogee. And
Okay.
this is the Kepler field. That's the
Oh,
classic Kepler spacecraft detector, because they scanned over Kepler. I mean,
I
this
see.
is the audience watching in the planetarium. The Hayden Planetarium has been closed since March, so we can't do these kinds of shows anymore.
But
But
the museum has reopened since then, right?
it just recently reopened. Yep. And it's at 25% capacity and following all of the right rules. But like employees like me, we're not going back. We're the only people that are working there that are back are essential to the everyday visitor.
Oh, like Neil deGrasse Tyson. He's back. He's just rolling
No,
in there.
Neil is definitely not back. Neil's on Zoom like the rest of us.
Okay.
Everybody's on Zoom.
Okay, let's see if
All right.
see if it works this time.
People look like they've figured it out here.
Yeah. So do you see answers coming in, or do you see?
Yes. It
Okay,
looks like
great.
the overwhelming solution is the North Star Polaris at 88%.
Yeah, 88%. Thanks everybody for bearing with us on that. Yeah. So it is not the sun. That was a little bit of a red herring. It is not Orion's belt. It is not the center of our Milky Way galaxy. It is indeed the North Star Polaris. Congratulations, everybody. So here is a handy finding chart, what we use in astronomy to kind of find our way around the night sky. And the Big Dipper is one of these really good map or pointer constellations. So you can see that the two stars, don't know how to pronounce them, Merak and Dubi. Cameron, do you know?
Merak?
Yeah.
Yes.
That I think Merak and Dubi is the way that most people say it.
Yeah. I'm not sure that that's actually the correct pronunciation, but that's what we say because
Right, I agree.
we're the worst.
And the North Star, for those who don't know, as you can see here, it's actually the last star in the handle, in the tail of the Little Dipper. And we specified, in the dipper of the Big Dipper, because you can actually use the 3 stars in the handle of the Big Dipper. There's a nice little mnemonic, probably not the exact right phrase, but you can follow that arc, and you can arc to a star called Arcturus that is very
Arc to Arcturus. That's right.
Easily located.
Just a quick mention. Unfortunately, it seems like there's some limit, and already we've reached it, and people can't go. We've reached capacity on the Poll Everywhere website. See, people are getting messages saying that it's at capacity. So we'll have to address that in future weeks. I'm sorry if you weren't able to get in. We still love you and your quiz answers.
Yeah, and please, if you're not able to answer it on the actual trivia, feel free to put it in the YouTube chat so we can see how everybody's answering back and forth.
Yes.
Yeah, thank you for letting us know about that. That's a good thing to troubleshoot. All right, we'll go to question 2 now. So question 2 asks, I discovered or co-discovered at least 8 comets and over 500 nebula and was awarded a gold medal of the Royal Astronomical Society. Who am I? So we have Hallie, Haley.
Hallie, I think.
Yeah, probably the same. I discovered or co-discovered at least 8 comets, Messier's in there, and over 500 nebulae. Buyan, I don't even think I know who that is. Kaylin Henderson, that is a great answer. I have not yet been awarded the gold medal of the Royal Astronomical Society. Isaac Newton. I hope Caitlin Henderson got a -1.
Well, what do you expect? I mean, geez.
Yeah. I mean, I did say I have not yet been awarded. Carolyn Herschel is coming in.
What about Bill Haley? That's a famous astronomer. Good old Bill. Just one comment after another.
Yeah, we're not on a first name basis. He's William, I think. Yeah, a lot of variations on Halley coming in. So the correct answer on some hail, okay. The correct answer, actually, it looks like it is not one of the more popular answers, is actually Carolyn Herschel. So here's a picture of her when she is 78. As I was reading her Wikipedia, I learned a lot of cool things that I didn't know. So she was the first woman to receive a salary as a scientist. She was the first woman in England to hold a government position. She was the first woman to publish scientific findings in the Philosophical Transactions of the Royal Society. And as the question mentioned, Carolyn Herschel was also the first woman to be awarded a gold medal of the Royal Astronomical Society in 1828.
I didn't even know they gave out gold medals. That's pretty sweet, though.
You might get a bronze, but yeah, they give out gold.
Yeah, well, I'm not saying for me.
And this image of her is the year after she won the gold medal. She also won some sort of medal from the King of Prussia. I had not heard of before. So yeah, Carolyn Herschel.
Good old Russia with a P. Yeah.
All right, so let's get to question 3. All right, the next total solar eclipse will occur on December 14th, 2020. So it's coming up. Mark your calendars. And it will be visible over what 2 countries? The next total solar eclipse in December of this year, so it's soon. Somehow it's almost October, so December's not that far away. Will be visible over what 2 countries? We've got...
I have a plane ticket to go.
Are you going?
I'm not going now, but I
Why
was
not?
going to go.
Just hold your breath for the whole flight.
Well, what? No, you guys are crazy.
I want to go.
Yeah.
I'm thinking about
this. I don't want to give it away, but this country.
You're giving it away.
Yes, that's right. Well,
I should say, we should have announced at the beginning, there's a whole potpourri of countries here. Please do not use your cell phones or your computers to look up the answer. I only say that because the correct countries did not appear until fairly late, or approximately equivalent to the Googling timescale.
Oh, I see Liechtenstein. Liechtenstein is on there.
Yeah, Liechtenstein, New and Zealand.
There's interesting. New York is not a country. Guam is not a country. Europe is not a country.
New York is like a country. So
yeah.
I think that.
Not a country. I assume that the South goes with USA, South USA.
It might go with America.
South Africa.
It says New Canada. New Canada might be a thing pretty soon.
Or Zealand. I really like Zealand.
South Russia.
Yeah, Georgia is both a country and not a country.
That's true. That is true. Is there a
It's also a name.
That's also true.
Yeah. There's some USA and Canada, Chile and Argentina also in the YouTube chat. So the correct answer in South America, drum roll please, is Chile and South America, and also Chile and Argentina in South America. So here is a really cool GIF that I think was actually made in 2000.
Yeah. I think I played that video game in the 90s, yeah.
I had to run Windows.
This looks like the Oregon Trail of
I love it. I love it. It's beautiful.
So you can see as it goes across the southern.
Yeah.
Wait,
it's going across. It's going across the south of, so I used to live in Chile. I lived there for 2 years because I was a postdoc there. And it's so pretty there. And it's going across the Lake District. And it's going to actually cross this awesome town called Villarrica. And Villarrica is where there's this big volcano. Some people might remember it erupted several years ago. I've climbed that volcano and stared down inside of the cauldron. And I want to go back and watch the eclipse from there, but I'm not going, Cameron. There's no way I'm getting on a plane.
You can drive.
Our flight was also, they actually canceled the flight that was supposed to take us from Santiago to the Lake District. So I think we've got
car-based. You got to drive. I'm driving. I'm going.
It's downhill, right? It's down.
It's downhill. It's south.
It's south.
The Earth is
just because you're going south doesn't mean it's downhill.
Oh yeah, that's right. That's right.
It has to do with the precession and the solar wind.
Oh, got it. Which way is right? Okay.
You gotta ride that Alphane wave. Surf that wave.
I'll say too, I looked it up because I didn't know too much about this eclipse. I don't know if these were answers without going back and looking. It will be visible as a partial eclipse from Bolivia, Brazil, Ecuador, Paraguay, Peru, and Uruguay.
Yeah, but partial eclipses are lame. You want the full.
Partial eclipses are awesome. They're just not as awesome as full eclipses.
No.
I like partials. I think partials are cool, but I do agree if you can get yourself to totality, you should go.
And totality for this one, I looked this up as well. So I was fortunate enough, maybe all of us were, to see the 2017 eclipse in August. That one had a duration during the maximum eclipse. That was 2 minutes and 40 seconds. For this one, it will be 2 minutes and 10 seconds. And it really is, you can see in this, Windows 95 GIF.
No, that's Windows 3.1.
It's peaking over the land masses, so that's really nice for the people who live down there. The April 8th, 2024 eclipse, which is going to kind of crisscross across the US, but go in the opposite direction roughly as the 2017 one. That one's going to have a maximum duration of 4 minutes and 28 seconds, so almost factor of 2, roughly longer.
Yeah.
So, everybody get buckled up for that one. It goes, I think, from kind of, it starts, I think you can see it in Mexico and then Southwest Texas, and then I think it goes all the way maybe up to Maine.
I'm buckled up.
Buckled up, ready to go.
I'm ready. 4 more years, and then
it's all gonna go off. It's gonna be crazy.
All right, so the next question, I'm just avoiding a 4 more years tangent. Planet 9, whose existence was hypothesized by Caltech professors Batigan, our very own.
Yes, Constantine.
And Brown in 2016, was recently suggested to instead be what type of object?
Notably, I'd like to note that this was not suggested by Batigan and Brown.
It's a good
type of
thank you for pointing that out.
We've got KBO, a Kuiper Belt object, black hole, long period comet, and brown dwarf. And we've talked about, I think, all of these objects.
Talked about all of them except for the black hole.
I think it came up briefly.
Did it?
Yeah.
Okay.
Just a few minutes ago when I said it. Yeah.
Okay. My mistake.
But so far, a black hole.
Yeah.
Run away with it. It's got about.
So here, I have to say, the article that proposed the black hole, while the votes are coming in, the best, perhaps the best figure in astronomy ever, which was it was a real life-size, demonstration of what that black hole would look like, which is, it was a black circle about this, size of a ping pong ball.
Yeah, that went viral. And I had friends outside of astronomy saying, did you see, figure 7 of, and I was like, you don't know anything. And there was a 5 centimeter diameter black circle as figure whatever.
It is. Yeah, it's a great figure. I love that figure.
It's so cool.
Yeah.
So as Constantine said, the answer is a black hole. And actually, I was going to borrow the same joke. Here is an artist rendition of what that black hole would look like if you're looking at a particularly blank portion of the sky.
Yeah.
But actually, the what is it? The radius would be roughly, if you had an Earth mass black hole, it would be roughly ping pong ball size.
Right.
Again, that
Oh, really? That's the event horizon is ping pong ball size for Earth mass?
Yeah.
Pretty small.
And so one thing I'll say just to plug, we were talking about microlensing a little bit after Jackie's talk. Here's an animation that hopefully is playing a little bit. So this is showing a general schematic for a microlensing event, well, for a lensing event. And so what happens is you have some object pass in between your telescope. This is showing the Kepler Space Telescope, your observer, and some distant background object, which we call the source. And this object that's passing between, which we call the lens, you don't care about how bright it is, but its mass actually bends the light from that background object. And if you had infinitely, telescopes that are able to infinitely resolve the sky, you would see that the light is not only amplified from this background object, but it's actually split in half. That's why you see it split into two images. And what you see is a background brightening. And so the articles of this author, who is not Batygin and Brown, they noted that one of the main microlensing surveys, it's the optical gravitational lensing experiment. It's a Polish survey run by a Polish group using a telescope down in Chile.
Oh yeah, Las Campanas.
Yeah, exactly, LCO. And they have found over the past couple of years, including one of Caltech's own postdoc researchers named Pajamik Moroz, a friend and colleague of mine, they found a bunch of very short microlensing events. So these are lensing events that last on the order of hours, whereas normal lensing events due to stars last weeks. And so they have hypothesized, the Ogle team did, the lensing team, that these could be roughly Earth mass splamos. Again, that's a significant.
You coined it and you're now using it as if it's a word.
Yeah. It's a word. However, what these other authors came along and said, is from lensing events, you really only know the mass. So you don't have any radius information. So you don't know if something is the size of a ping pong ball, if it's the radius of the Earth. And so maybe it's possible that these short timescale microlensing events could be caused by low mass or potentially even what are called primordial black holes. Kay and Jackie, what are your thoughts on the black hole Planet 9 hypothesis?
Well, I will defer to my colleague, Dr. Faherty on this one.
You don't want to give your take?
No, I mean, look, so actually I will say this. So if we play kind of devil's advocate, all that our models can tell you is that something has the mass of about 5 Earth masses and has an orbit of such and such. It could be a burrito, it could be a black hole, it could be a planet, it could be, a hamburger, it could be a ring of material. All of those things will have the same gravitational effect as far as the data are concerned, the data from which we infer the existence of this object. So in principle, everything is fair game. It would be really dramatic, right? If we search the night sky down to some really high magnitude, right? To some really deep, depth, for lack of a better word, and we don't find anything, but the data patterns continue, right? The notion of this clustered distant Kuiper belt and everything continues to fall into place, but we don't see the thing that's causing it. I mean, that is the moment to really step back and to ask the exotic question, is this being forced by something that is outside the realm of what our imagination kind of readily gives, like a dark matter halo or whatever of the sun? Because after all, Leverrier, who discovered Neptune through mathematics, predicted another planet called Vulcan that's not there, but the effects of Vulcan, namely the forced precession of Mercury's periaps is in fact a relativistic effect that was resolved later by modification of gravitational theory. So, I think that's when we begin to ask these really more exotic questions.
I do think, I would say, crazy ideas, or ones that like we very quickly dismiss because they're so crazy, that's both, it's an appropriate response at times, but also, to your point, Constantine, too, on this, like, that's also how we can keep moving forward. I completely encourage crazy ideas that we can then beat down in the scientific process to say, could it be, could it be, could it be? It's like anything, the Carl Sagan line, extraordinary claims require extraordinary evidence. But I think everybody in their career as a scientist should make like between 10 and 1,000 extraordinary claims.
Whoa.
Just to get them all out.
That's a lot. That's like Avi Loeb, a lot.
I just think,
well, maybe not that crazy.
I'm just hoping it's a burrito.
You are both making me think of, it's kind of the intersection of, it's the town that's in between where William of Ockham lives and Bertrand Russell lives. So William of Ockham, famous for Occam's razor, says, the simplest explanation is most often the correct one. And Bertrand Russell, one of his famous quotes refers to, he's talking about if you put a teapot in orbit, close orbit around the sun, it would be very difficult to prove that it was there. But he would say that the burden of proof lies on the person who's making the unfalsifiable claim. And I think exactly what you're saying, Jackie. The scientific process is going to be what guides, whether or not it's a burrito.
I'm saying the intersection of the Venn diagram intersection point, it says burrito. It's just a burrito.
It says
that's what it says.
I mean,
I'm so hungry right now. You guys are just driving me crazy.
SoCal, like you gotta like this is the LA astronomy on tap. Okay, I feel like
What does that mean? I don't know what that means. What does that mean?
It means it's a burrito and the hot sauce is gringo bandito.
Okay.
And for those of you who are taking notes at home, burritos, and this is true, before you have eaten a bite out of the burrito, are topologically equivalent to pies before you have sliced the pie. This follows the cube rule. They are also equivalent to Pop-Tarts, but they are not equivalent to sandwiches or hot.
And there's Pop 3 star outputs in them as well. So got the first stars.
That's true. All right. Let's
move off our next Oregon Trail graphic so that we can get past this 1985 CG.
All right.
Ooh, this is a good one.
Mount Wilson has thus far survived the Bobcat fire. When I was writing this question, Cameron had a good tweak, which was not that it has survived, that it has hitherto survived.
Thus far. Hopefully, they've been doing some really proactive burns around the observatory to, phase off any burning that could occur in the future. But it's not a done deal that it's there forever so far.
I should say we thank if any of you are listening, the Monrovia firefighting department in particular, but really all of the people who have been deployed and are fighting the fires, Bobcat, Ranch 2, and out there. We appreciate your service, and especially as regards to human life, but also our Mount Wilson Observatory. So the options, which of these major discoveries was made at Mount Wilson? Expansion of the universe, getting about almost 2/3 of the vote. Pluto, hanging in there. I'll note that somebody earlier in the chat said when Planet 9 is discovered, can it be called Pluto? Since we already have Pluto, which I think obviously is the answer. Sunspots or the cosmic microwave background, or CMB. Only one of these. So the answer indeed is the expansion of the universe. So I'll just say, give a little bit of a history lesson. I was looking this up earlier today. So Mount Wilson Observatory has held the record for hosting the world's largest operational telescope for several decades. So it had the 60-inch, which achieved first light in, it was December 8th, 1908. And it, when it came online, was the largest optical telescope in the world. And then 9 years later, in 1917, the 100-inch came online, and it took the title of world's largest telescope. And it held it for 32 years until 1949. Something I didn't know is that it was another factor of 2. The next world's largest telescope was 200 inches, and it's 200 inch at Palomar. So actually, you know, that title has been in, had been in Southern California for many, many years in a row. And this is a picture of, does anybody know who this is? Looking through the 100-inch.
Edwin?
Yeah, Edwin Hubble. So he made 2 major discoveries using the 100-inch at Mount Wilson. So one was he found, by taking the most detailed images of nebula, he found out that not all of these nebula, these fuzzy spots that other people had found, were inside the Milky Way galaxy. And then, in fact, some of them were so far away that they had to be outside the Milky Way. And this led to you know, understanding that there are other galaxies external to the Milky Way, which really expanded our understanding of the distance scale of the universe. The second, which relates to the trivia question, has to do with he looked at Cepheid variable stars. So these are stars that they pulsate, so their radius changes. It gets bigger and smaller and bigger and smaller. And they do so with a periodicity, a certain characteristic periodicity, as well as an understood relation between their periodicity, how long before they, you know, expand in and out, and how bright they are. And so he could use this and map out the distances to these Cepheids on all these different galaxies. And that led him on the path to understand that the universe was expanding.
Good call.
Amazing that.
Kalen, I have an interesting side trivia on Mount Wilson, which is, and I'll put the story in the chat, which is that they went back and looked at all the photographic plates that had been taken once Pluto was discovered.
Brown dwarfs everywhere.
No, they had a pre-discovery image of Pluto. They could have found it.
Really?
Wow.
Yeah.
Yeah.
I thought you were trying to trick everybody by putting that in there.
Image of Pluto dates back to like 1909 or something, right?
Really?
Yeah, it's really quite early in that whole debacle. Yeah.
Scooping Tombow, that poor guy.
Once you know something's there, it's very obvious.
Actually, I should give a proper shout out to my partner in crime, Mike Brown, who of course discovered the biggest, you know, Kuiper Belt objects, you know, in the last 20 years or whatnot. You know, a lot of the stuff that he found with the Palomar Observatory, and he reconstructed the orbits by going back to plates from, you know, dating back to like the 50s, right? And the images were there. I think Eris in particular, I may be misremembering, but I believe Eris was one that he found dating back to, you know, 1950s, right? It's a
really,
yeah.
Whoa.
So I'll say
cool.
and I'm going to get at least one of these wrong, so people correct me. So Pluto, discovered by fellow Kansan Clyde Tombaugh.
Oh, jeez.
Out in, not at Mount Wilson, Lowell, right? In Arizona.
Lowell, in northern Arizona.
Yeah.
Flagstaff.
And sunspots, was that Galileo or earlier?
Yeah. Galileo was the first person to take a telescope and point it up. And he, don't do this at home. Don't point it at the sun, FYI. But
yeah, Astronomy on Tap did not tell you to point it.
Yeah, and was able to be the first person to really detect localized dark spots on the surface of the sun.
You know what I say? I say I throw my telescope in the air sometimes, saying "Ayo, Galileo."
Oh, God.
Oh, okay.
Quotable, very quotable.
Yeah, straight from, I don't know, 2011, maybe 2010.
That's a Throwback. And then let's see, CMB, that was Penzias and Wilson. But then the
77-ish?
I'm looking it up right now. A Nobel Prize in 78. The discovery in 65.
Oh, really? Okay. All right.
Yeah. And then the kind of famous image that really mapped it out is from a spacecraft called WMAP, the Wilkinson Millimeter Anisotropy Probe.
Yes, very
Microwave.
good.
Microwave. Oh, I knew I was going to get one.
Boom.
All right, question 6.
Oh, that's a good one.
Okay, on October 20th, 2020, Illuminati confirmed, NASA Rex will land on an object named Bennu, I think it is, and begin to collect samples for return to Earth.
So can I tell a quick fun story about this?
Yeah.
It will not reveal an answer, and it can fill the time as people fill it in. That OSIRIS-REx was launching. Several people that work at the American Museum of Natural History are very, very involved in this mission. So I was in contact. What?
Is Denton?
Denton is, yes, Denton Abel is. And then a couple of research associates that are from CUNY. And so I was super excited about the launch, and my dad, who's a pilot, was flying around Florida, coming home that day. And whenever there's a rocket launch, they'll tell you, like, you can be a small pilot, but clearly you can't be around it. And my dad sends me this text with a picture. He's like, Jackie, this is so weird. What do you think this is? And he was in the air flying near it and got a shot of the rocket taking off and coming. Whoa. Yeah, it's such a cool shot. And I was like, Dad, that's OSIRIS-REx. You just watched the launch of this amazing rocket that's going to this object called Bennu, but I won't tell you what kind of object it is. And I was like, it's a return sample mission. It's gonna be so cool.
Wait, do you have the picture? Can you show us the picture?
I do have so I have the picture. I have to dig it up. But so it's kind of funny about this. Like, I was like, this is so cool. But this was years ago, right? Because it launched years ago. And I recently did a YouTube thing with some of the people from OSIRIS-REx, and they were doing the presentation, and I was monitoring the chat and like answering questions. And the guy says, "Oh, I know you." The PI of the mission was like, "I use your dad's picture all the time because I had texted it to a friend who texted it up the chain, and it gets used in all the OSIRIS-REx talks because it's such a cool shot."
That is cool.
That just happened. My dad took it with his camera phone. He's just like, "Oh, look at this rocket going off." I thought that was pretty cool. I feel famous because I know my dad who took the picture.
And does he know? Like, does he know that his photo is famous?
I told him the other day, I was like, because he's, that's the kind of thing that makes anyone feel good. And he like patted himself on the back, like, took a shot, gets used to tell the public.
His planetary science career will forever be better than mine because of that photo.
So the crappy part is that the credit on the picture always goes to me, not him, because I shared the picture. So I started to correct that. Like, no, you should correct it. It shouldn't be Jackie Faraday. It should be Richard Faraday because he's the one that took the picture. So there you go.
Very humble. Thank you for sharing your modesty.
No, that's wild. That's really cool. Well,
I am being modest.
I know that you are. You are.
I don't need the credit. I didn't take the picture.
The correct answer, which it turns out the vast majority of people did get, is asteroid. So OSIRIS-REx, this is a mouthful. It stands for, so this is an artist's conception of its close approach to Bennu, the asteroid. OSIRIS-REx stands for the Origins Spectral Interpretation Resource Identification Security Regolith Explorer, or OSIRIS-REx. Based on where it is, where the asteroid is, it takes signals 18 minutes to go one way from Earth to OSIRIS-REx. So the way what it's gonna do, it's gonna do this, in just like 3 weeks, a little bit over 3 weeks. It's going to get really, really, really close to the surface of Bennu. It's gonna blast it with nitrogen gas. and then a little bit of Bennu is going to come off. And it's got some sort of, I don't know actually what the device is, but a scoop or something, and it's going to collect, what do they want? 60 grams is the goal, or about 2 ounces of material from Bennu.
It's got one of those arms like the things you find in gas stations that like scoop into the stuff and exactly. Yeah.
They do have I think a second chance and maybe a third chance if either the first this first very nearly touchdown approach doesn't work. I think they have a couple more chances, but then it will leave from Bennu in 2021 in March, and it's going to land in the Utah desert. Make sure, Jackie, that your dad is taking notes. Lands in the Utah desert in 2023. So can road trip there and then road trip back for the eclipse in 2024. And here, this is actual data. This is from one of the cameras on OSIRIS-REx. This is not of its closest approach. That hasn't happened yet. That's in October. But that is what the asteroid Bennu looks like. This kind of footage is absolutely mind-blowing to me. I think
it is mind-blowing.
And I'll say too as well, we have featured Hayabusa and Hayabusa 2 at least once, I think twice this year.
Yeah.
On the program. So that's a Japanese series of missions. This is NASA's first asteroid sample return mission, but Japan actually brought part of an asteroid back in 2010, and they're doing it again, Hayabusa 2, that's expected back in December of this year, I think December 6th or something.
Cool.
Very cool. A lot of countries in the game of asteroid sample returns. It's it's the next.
And you said it's 2 ounces?
Yeah, for OSIRIS-REx, yeah.
The first pass, but then there will be multiple passes.
If I'm remembering right, I think they will not do multiple passes if they get enough sample on the first pass. I think that.
Well, you do know, it's 40 ounces to freedom. So.
Hey, you had that glint. I just wasn't sure where this was going. Oh, it's fun. All right, question 7. So phosphene,
All right.
a potential biosignature, was found in clouds in Venus. In what other places has it been found?
I almost gave this away earlier.
Interesting take.
White House, Jupiter, guts of microbes. Let's see what we got in the YouTube chat. Can we beat Germany?
I like this automatic this write-in response. It's different. It's definitely special.
You get a real take that way.
Then you really know what people are doing and who's left here.
Germany. Yeah.
It is very different.
I mean, you just see it's getting later too. Well, for you guys, maybe it's not as late, but it's getting later. People's answers should start getting wild.
Just, crazy.
Just let it out, everybody. Tell us what you really think. Where do you find this phosphene?
Well, so some people are letting loose in the YouTube live chat. So we got Jupiter and Saturn.
Is penguin poop?
Jupiter, there's penguin poop.
Penguin poop. There's going to be multiple right answers to this. Or are you going to only let one, Kaylin?
Oh, this is a right-in. I actually don't know the right answer. That's why I specifically made it a right-in. We're letting.
Wait, what?
This is majority vote. Where did we find it?
I'm pretty sure that's not how science works.
Yeah, we can't do that. We have to follow scientific principles.
The 7th question, science goes a little left. All right.
I should say everybody should follow Clara Suva Silva on Twitter. Her
phosphene champion.
Yeah, so she wrote her PhD on phosphene, and her Twitter handle is Dr. Phosphene. So if you want to know all about phosphene, you should follow Clara.
Yeah, we should have her on here. Talk about.
We should definitely have her on. She's awesome.
Dr. Phosphene is a dope name too.
Yeah, it is. You wish you have that handle, right, Kaylin?
I do. Right after orthogonal.
Okay.
No. So people should also look up
Underdome.
Speaking of centaurs, we were talking about the centaur of attention. There is a reverse centaur. So when you create a centaur, you have a human and a horse, and you use half of each to make a centaur. A reverse centaur is using the other half, and you make a creature. There's also the recursive centaur, which people should Google image, make sure Safe Search is on. Just because puns, wordplay, fractals.
Wordplay.
Mhm.
So here, this is a composite image. This is taken of actual data of Venus. This is from the Akatsuki, another Japanese spacecraft actually that's studying the clouds on Venus. This one in particular, I think, is a very beautiful image. And the brown region in particular is where you have these convective clouds churning in the atmosphere. So
I think this is the mission which had a problem when they launched, and they had to send it around the sun for 5 years while they fixed it, and they weren't sure it would work again, and then they got it back, and it started sending these amazing pictures.
Exactly. They were going to do initially the goal, and I don't know exactly what happened, was to put it in, have an orbital insertion around Venus. And something went left. And so now, I can't remember exactly, Jackie, maybe you know, I think it's in some like, it might even be an elliptical orbit. I don't know if it's around Venus or if it's actually, I don't know what it is, but it's very different from the planned orbit. But at least the closest approach, it's still able to study Venus.
I just wanted to give a shout because I started getting text messages from people that were watching this, and Miki Nakajima is watching, and she is from Japan. But she's she's a faculty member at Rochester, and Mickey is the one that got me really excited about this mission. So the one that can answer this is Mickey. If you're in the chat, you should talk up.
Oh, yeah,
talk up JAXA. Talk up this one.
I have to say, Mickey and I were grad students together, and really Mickey should be on this because she should. Awesome. She knows.
All right, we'll make it happen.
Ton of stuff. Yeah, I have nothing but respect
in the text right now.
Yeah,
she's the best.
I love
and she's the best, and she knows. She can also talk to you about how the moon formed, as well as what Phobos and Deimos are around.
Those enchiladas
around Mars.
Enchiladas.
I was gonna say, but they look like potatoes rather than enchiladas. I mean, you're in LA. I don't know what your brain is doing, but
I haven't had dinner.
You'd be the host with the D-most. It would be great.
Wait, I don't get that one.
All right, pun master.
What was I going to say? Oh yeah, so this is Venus. This is where phosphene was found.
Right.
Phosphene is a potential biosignature, but one of the questions a lot of biosignatures raise is, can it be produced inorganically as well as organically? I don't actually know the answer for phosphine.
I do.
What's the answer?
Well, according to the paper, not because I do any research in phosphine, according to the paper they put out, the answer was that you can produce phosphine in the interiors of gas giants like Jupiter and Saturn, and then through convection, you kind of stir it up and bring it to the surface. But for terrestrial planets like Venus or the Earth, the only time that you can produce this is through organic means, through life, like microbes producing this. So, you know, I kind of have a beef with all of the sensationalist news media saying, "Oh, we found a life, you know, a biosignature in the atmosphere of Venus," because it could also be that there's something that we just don't understand about chemistry, the chemistry necessary to produce phosphine. But that doesn't sell newspapers. You can't say, "Hey, everybody, look, I'm going to put it on the cover of the New York Times that we've detected a new mechanism for generating an organic chemical through different chemistry pathways." Like, that's not going to sell anything. But, you know, that's probably a more realistic explanation for the presence of phosphine in there. I mean, don't get me wrong. You know, in 10 years, when everyone's like, "Oh, let's bow down to our new intelligent overlords in the surface of and the atmosphere of Venus," okay, I'll be the first one to admit that I'm wrong. But
Right. Yeah, you will. You
So-
will be rated in
It's too late by then. Yeah. They'll be like,
Season 2 of The
what
Expanse.
were you thinking? Yeah.
There was a paper that I think it might have come out yesterday or maybe today, and it's been a lot of conversation about volcanoes and that you can get phosphine out of geologic activity.
Okay.
And that that there might be signatures and signs that it's active volcanism. And yeah, who knows?
All
But
right.
I'll
Well,
tell you, do you want to know what
let's
has
let somebody else
phosphine
go.
though as well? Wait, do you want to know what has phosphine as well?
Tell me.
Germany.
Brown
Good
dwarfs.
news.
Frickin'
Oh.
brown dwarfs, people. We have phosphine because Jupiter and Saturn do have it, and it's a little confusing why they do, because it's disequilibrium chemistry. You should not have it where they have it and how they have it. Just
So Venus is a
rules.
brown dwarf. That's what you're telling us.
Well, I mean, if you're a gas giant, you're super different than a terrestrial planet that has like an atmosphere that you kind of know is carbon and oxygen. So you got to like shift up the phosphine somehow. Like, how'd you just put it all in the? How'd you generate all of it?
Shift it up. Shift it up. The phosphine.
Yeah.
Yeah, I'll have these NOS tanks. Only it'll be phos tanks. It's gonna be great.
All right. Okay.
So I will say, building off of Cameron, what you were saying, so Jesse Christensen, a friend of the program, an exoplanet scientist and colleague of ours at Caltech, she had a great tweet shortly after this came out. And she said and this kind of harkens back to our discussion about William of Ockham as well. If it comes down to explain some sort of new detection that we found in a planet, I'll take unknown chemistry or unknown geology or unknown biology every time. Unknown biology is probably the least likely explanation. Not impossible, not implausible, but that doesn't sell newspapers.
Right. It does not.
All right, question 8. What significant event, activate. What significant event happened about 380,000 years after the Big Bang?
Ooh.
When was your birthday? What year?
Oh, that's cruel. That's too cruel.
We have light decoupled from normal matter. The first stars formed. There's a major supernova in our Milky Way galaxy where life began on the surface of the Earth. 380,000 years after the Big Bang. This is not 380,000 years ago.
Phosphene formed.
Phosphene.
Shift it up. All right, first stars forming is really, really running away with this one.
Nobody likes supernovae. Jeez.
Nobody likes light, supernovae, or life. People like stars. More of a stars crowd. Well, hate to break it to you, stars crowd.
Yeah. Word.
Not the correct answer. The correct.
Can I talk about this one? I really like this one.
Yeah, take it away. Take it away.
Okay, so on my drive back from Great Dune National Park today, I was thinking about how to explain this. So if you think about the age of the universe, how long has the universe been around since today? Many of you may know it's about on the order of 14 billion years as opposed to this 380,000 years. So it's much, much longer. And so the early universe, today we think of the universe, you think of clumps of stuff. So you think of like a star or a planet that's really high density, and then the space in between a planet and another planet or a star and another star is just a big vacuum with very little density. But in the early universe, it was just kind of like a fog, kind of like a soup of stuff that was generally uniform in density and not a lot of voids in between stuff, and generally at a really high density, right? So the matter, the stuff, protons and electrons and hydrogen atoms was so to say that it was coupled with light, radiation, photons flying around, and everything was so dense that photons would regularly impact your protons and electrons and atoms, and there was this interaction that would take place where a proton and electron get close enough together to each other that they form a hydrogen atom, but then they get smacked by a photon and they break apart. And this is happening constantly in the early universe. But the universe, as we all know, thanks to people like Edwin Hubble and discoveries made in the last 100 years or so, is expanding outward. And as it expands, the density gets lower. So think about that thick pea soup fog that's there. And over time, it's just thinning out because the universe is expanding, but the mass is the same. And over time, that thick pea soup fog gets low enough density that finally at some point you can kind of see through it. And that's essentially what happens. The photons that are flying through your early universe get stretched and less energetic as they stretch, and finally they're unable to break apart these hydrogen atoms and they just kind of free stream. And what that means is the picture that we're seeing here is the map of the cosmic microwave background. That's the photons that eventually, when the universe reached this expansion rate where the photons could just fly straight without being energetic enough to break up hydrogen atoms that were forming, they just kept flying indefinitely. And we can record that with our telescopes. And it shows us what that radiation field looks like from just after the Big Bang, which is, like I said, according to this question, it's about 380, 400,000 years after the Big Bang, which is really a very little, a very short period after the Big Bang compared to where we are now. The universe was in its infancy, and those photons have just kind of been flying around since then. But what it means, though, is we can't look farther away than that distance because the fog, the soup of stuff is just too thick, and we wouldn't be able to record any information from that period because that's when matter and light are essentially coupled at that point. Sorry, that was.
Yeah, and I'll add just a couple of things, which are, I mean, that was an awesome explanation. This is just to kind of build off of it. This image that we're showing, we referenced it earlier in the show. The difference in temperature from the red spots, which are the hotter spots, to the dark blue spots, which are the relatively cooler spots, is 0.0004 degrees. So, there are these hotter and cooler spots in this map, but actually the amplitude is less than 1/2 of 1,000th of a degree. And so you have this relatively uniform, kind of even, soup as Cameron's describing. And to answer a question that is in the chat, actually, that I'm seeing in the YouTube. So somebody's asking, so the light is separating from the matter. So what's happening is, at this point of recombination, and recombination is kind of a misnomer. I generally think of it as maybe combination. So you've got these electrons and these protons zooping around, and a proton just by itself is another way to think of it as an ionized hydrogen atom. And so at combination, or what's really called recombination, the electrons and protons become bound. So now instead of electron over here and proton over here, you have a 2-particle system where the electron is bound to the proton, and just kind of the way it works, it's most efficient for the electron to be bound to the proton in its highest energy state. That's kind of the easiest for the proton to capture. And then what will happen is that electron will very quickly go down to its lowest energy state. And in transitioning from a high energy state to a low energy state, that difference in energy means that a photon will be emitted. And so that's what we're seeing. And that's what's creating this soup. So I hope that helps with the question.
Yeah.
Great explanation. That was good. Oh, and another thing I learned, this was actually a few weeks ago, totally separate from looking up questions for this. I don't know if the rest of the panel knew this. I definitely did not. So, so the thing I did know, hydrogen has has multiple isotopes. So an isotope of a given atomic element, it depends on how many, what's your number of neutrons, which changes how many total nucleons you have. So hydrogen always has exactly 1 proton, but there are 3 different isotopes depending on how many neutrons you have. If you have 0, 1, or 2. And I didn't really realize this, but hydrogen is kind of the name, this is probably true for all elements, to kind of the family of single proton elements, single proton isotopes. So if you have 2 neutrons and 1 proton, you're tritium, because you have 3 nucleons. If you have 1 neutron and 1 proton, you're deuterium for 2 nucleons. And protium, if you have no neutrons, 1 proton, and so 1 nucleon, that isotope, which is far and away the most common, is called protium. I did not know that that it actually had its own name that was separate from hydrogen. I had never thought about that.
Just as an aside on that, Kellen, we mentioned deuterium earlier when we were talking about the Brown Dwarf to planet boundary. And that's often referred to also as heavy hydrogen. And it's a different boundary because you need, you can have a lower temperature to get that to burn. Hydrogen burns at a very specific temp to get it to fuse and turn into a nuclear engine. But deuterium, heavy hydrogen, which certainly exists when you inside of stars, it's just a lower temperature, so you can get that to fuse for a little bit of time too. But yeah, there's a family of hydrogen.
That's right.
Yeah, that's very cool. And
No
usually
quadrium though.
Are referring to hydrogen, they're referring to protium, this no neutron single nucleon isotope. Yeah, very cool stuff. All right, let's go to
How many more questions do we have? We're going on forever. We're way over.
All right, question number 9 out of 10.
Okay.
There are many seas on the moon, but there is only one ocean. What is it?
Ooh.
So we've got ocean of storms, topographic ocean, ocean of fire, Jam Gabar, or ocean of dreams.
Oh, the Jam Gabar. Yes.
Interesting choices here.
Interesting. Yeah, Cameron and I may have modified the choices.
You did. No, it's good. It's good. Some good ones here.
Some good ones here. I really like it. So ocean of storms, people are liking. Ocean of dreams, people are really liking. Jam Gabar, getting some traction from the.
He likes topographic ocean. Jeez. Haters.
Ocean of fire. One person does. All right.
I'm pretty sure there's no ocean of fire on the surface of the moon, though.
Would there be ocean of storms?
There's not a lot of clouds there either. Constantine, weigh in here.
My feeling that Jam Gabar is the answer. Okay, like, that's clearly the one.
Isn't Jam Gabar the poison from Dune?
It's not the poison. It's a needle. You stick your hand in the box.
Oh, right.
And the Bene Gesserit, which holds the Jam Gabar to.
I thought it was the poison on the needle, but it's the needle itself.
Yeah, Cameron, get it right. Okay. It's just, yeah, I can't.
Yeah, Cameron, it's getting a little late. You might want to sign off.
Yeah.
I mean, look.
I have the latest hour. You guys are still on regular time.
That's true. That is true. Jackie's here.
All right, we'll get this one over. So I'll say Tales from Topographic Ocean. So this is the 6th studio album by the English prog or progressive rock band Yes.
Oh, yes, owner of a lonely heart.
Owner of a lonely. So different album.
Prog rock.
Topographic Oceans was released on December 7th, 1973. So their first album, the eponymous Yes. Then there was Time in a Word, the Yes album, which is separate from Yes. Fragile, Close to the Edge, and then Topographic Oceans. I'll note that this is the first album with Alan White, who actually replaced Bill Bruford on drums.
You've really outdone yourself, Kaylin.
And it's important that this is a concept album. It was actually a double album.
Oh my
it was conceived while they were on tour in Japan. And I think it was Can't remember. No, Rick Wakeman.
Stop. Just stop. It's late. We don't need to hear the minutia of Yes, the band.
Philistine. Fine. The answer was not topographic ocean.
This isn't even the right answer. You had a slide for the wrong answer. That's so funny, Kaylin.
Yeah.
I don't know what the right answer is.
If anybody would like to talk yes, just chat in the thread. And we can take the prog rock on a side quest here. Anybody else likes 20-minute songs?
The correct answer is Sea of Storms.
Is Ocean of Storms, Cameron. It's Ocean of Storms.
I'm sorry, Ocean of Storms. You're correct. Okeanos Procularum, because in Greek they don't say soft seas. It's Okeanos, not Oceanus.
Cameron, I feel like you're getting distracted from topographic oceans.
I'm sorry. I really got caught up in the prog rock band. Yes, that was really too much for me.
All right, we're going to get Cameron back in on this last question. So, longtime fans of the program know that we always have a Star Wars question. In the
Star Wars shirt.
In the documentaries of the Star Wars, Luke Skywalker trains with Jedi Master Yoda. So we have fans of tax law in the audience.
I'm so glad I stuck around. I'm just
I don't even know what this trivia is. This is crazy.
I assume $750 is a reference to the amount that somebody's president paid taxes in 2 consecutive years. We've also got Tatooine, Dagobah, Gallagher, Barstow reappearance, Gerbil, topographic ocean.
Oh
That's
goodness.
We're ending on a high note. Vulcan.
Fear is the path to the dark side, Kaylin.
I have chosen enlightenment. You have chosen fear. I've chosen illumination, enlightenment, and ultimately nirvana. But you can stay. The correct answer, thank you everybody, is Dagobah. So here is, again, and this is real data taken from the Wikipedia archive. Dagobah.
No, Kaylin, it's Dagobah. Luke Skywalker explicitly says the Dagobah system in Empire Strikes Back. He doesn't say Dagobah, so stop it with that.
Yeah, Luke Skywalker is some backwater farm boy from Tatooine. I'm not going to trust him over Wikipedia as far as how to pronounce the system.
It doesn't give a phonetic pronunciation on Wikipedia. Thank you very much.
Oh, because
I wrote that article.
We'll agree to disagree on this point.
Was it Wikipedia or Wookiepedia? I'm confused.
Wikipedia.
So Wookiepedia is different than Wikipedia.
Yes, it's the Star Wars, central compendium of information.
I see. I'm sorry, I'm not as literate in as apparently the others are. It's just maybe they have phonetics on Wikipedia, maybe not on Wikipedia.
Well, I guarantee it's not Dagobah.
Yeah, I said based upon what Cameron said, it's less different than you'd think.
All right, they do not have phonetics. So I think that means we're gonna have to agree to disagree.
No, I can find a video clip of
some farm boy who's living outside the outer rim. I don't need to hear that bullshit. This is outrageous. So Dagobah is a system with one eponymous planet shown here. So this is actual data, again, pulled from the archives. It is roughly 50,000 light years from the system to the core, which is about twice from our sun to the center of our own Milky Way galaxy. So the Dagobah system is actually about twice as distant from the center of the Star Wars galaxy from the documentaries. All right, thank you everybody for playing. Prizes all around. We all learned a lot. We shared a few laughs. Cameron even learned about Dagobah. So
yeah. Oh God. it hurts my ears. I don't know what hurts my ears more, to hear you say Dagobah or to hear you lecture about Yes, the band, the band. All right. Well, thank you to our speakers tonight, Jackie and Constantine. Excellent talks, excellent discussion. Very much appreciated. Thank you, Kaylin, for your wide knowledge of Dagobah and Yes, the prog rock band from 1982.
Not just from 1982. They are actually still, with many of their core members, still touring, producing albums. I think Rick Wakeman has also done.
Thank you, Kaylin. Thank you.
He's done his own solo career.
Our next event, the next Astronomy on Tap, will probably be around the 18th. I'll put it on the YouTube channel and on social media. Our next Caltech Astronomy public lecture will be a week from Friday. It will be Dr. Agnes Ferte talking about dark energy. What is it and what implications does it have for the evolution of the universe? And yeah, I think that's it. Stay safe, wear a mask, vote. All of these things are good.
Fill out the census.
Yeah, do the census if you haven't already filled out the census. It takes like 2 minutes.
I'll note too as well, while we're on that subject, Yes has also been elected into the Rock and Roll Hall of Fame.
All right.
My goodness.
Oh, okay. All right.
Can we do a screenshot picture for Twitter and everybody at home can smile too, as if they're in it? Ready? 1, 2, 3, smile. Okay. And I hope people at home watched and smiled, and you can tag yourself.
I hope they were smiling. I hope they were smiling as well. Oh, one last point. Caltech Astronomy is going to start putting their colloquia on our YouTube page. So there will be very high level astronomy talks at the level of what we as professional astronomers and astrophysicists watch. So I will update our YouTube page with those over the next few weeks, but we'll have one a week for the next like 14 weeks. So feel free to join in. They will not be live streamed. We will not be monitoring the Q&A for the speakers, but these will be at a very high level. So if you're really feeling like, yeah, I really want to hear more about Planet 9 is a black hole, or
gift up the phosphene to the max.
I want to learn so much more about Yes, the prog rock band from 1982.
Well, they have not invited me to give a colloquium yet.
Anyway, thank you to our audience for showing up for us to mess around and drink beer and talk about science, but it's been fun.
Hi, everybody. Thank you.
Bye, everybody.
I got to figure out how to end this stream. Okay. Stream ended.
I'm so glad.